The world is breaking its own rules over and over again somewhere out there. Space isn't just big, it's also violent, strange, and much stranger than fiction. Stars spin so fast that they almost tear themselves apart, and explosions shine brighter than whole galaxies. We're going to look at some of the strangest things that have ever happened in the universe. These are real events that happened when nature pushed itself to its limits and dared us to explain them. It's not science fiction. This is the harsh and scary truth about the world. GRB 200826A, the identity crisis burst. Scientists have a set of rules for gamma-ray bursts. People think that the short ones, which last less than 2 seconds, are caused by neutron stars smashing into each other. Long ones, lasting more than 2 seconds, normally happen when a very large star falls apart and turns into a black hole. However, in August 2020, something called GRB 200826A broke those rules. This burst lasted only 0.65 seconds, which would normally make it a classic short gamma-ray burst. But as scientists looked deeper into the data, things got weird. This wasn't the kind of burst that comes from colliding neutron stars. It had all the fingerprints of a collapsing massive star, the kind we usually see in long bursts. This confused astronomers around the world, and they nicknamed it the Identity Crisis Burst. So what really happened? The event was picked up by NASA's Fermi Gamma Ray Space Telescope on August 26, 2020. Immediately, researchers flagged it as a short GRB based on its duration. But something didn't add up. Its energy profile, the afterglow, and even the host galaxy where it came from didn't fit the neutron-star merger pattern. Follow-up observations showed that the burst came from a galaxy about 6.6 billion light-years away. In that galaxy, there was evidence of recent star formation, something typical of long GRB host galaxies. Even more suspicious was the detection of a faint supernova-like glow appearing days after the burst. This faint light, dubbed a kilonova impostor, wasn't strong enough to be a full-blown supernova, but hinted at the death of a massive star. But wait, why would a massive star die in under a second? That's not how this usually works. Here's where the physics gets strange. Scientists now believe that the kilonova impostor was a failed long GRB. In other words, it was a star collapse that tried to produce a typical long-duration gamma-ray burst, but something cut it short. One theory is that the star's collapsing core formed a black hole too quickly, swallowing the jets of energy that usually power a long burst. What we saw, that tiny 0.65 second flash, was all the energy that escaped before the black hole slammed the door shut. Picture someone putting a rock wall in front of a fire hose right after it starts to spray water. That's what took place. The energy began to explode, but the black hole formed so quickly that it stopped the explosion in its tracks. This wasn't just a weird one-off event. It forced scientists to rethink the way we categorize gamma-ray bursts. Before this, the entire field relied on a simple classification. Time. Less than 2 seconds? Must be a short GRB. More than 2 seconds? Must be a long one. But the kilonova impostor proved that time isn't enough. You have to look at how the burst behaves, where it comes from, and what kind of light it leaves behind. After this discovery, astronomers began looking back through old data, and guess what? They found more examples of these identity crisis bursts hiding in plain sight. It turns out kilonova impostor might be just one of many that blur the line between what we thought were two completely different events. It also means a lot for the study of gravity waves. Along with gravitational waves from neutron star crashes, a lot of short GRBs are looked for. But if some short GRBs really do come from stars collapsing, we might be waiting for signs that will never come. And then there's the matter of population. How common are these failed long GRBs? They might be more frequent than we thought, but they're harder to detect because they're shorter and dimmer. The kilonova impostor was relatively nearby in cosmic terms, which is probably the only reason we caught it at all. Swift J 1818.0-1607, the hybrid star. In March 2020, astronomers detected a cosmic oddball that instantly shook up our understanding of neutron stars. It was discovered by NASA's Neil Gehrels Swift Observatory, and it got the clinical name Swift J 1818.0-1607. But what really made it famous was its behavior. It acted like two different types of stars at the same time. So what exactly is this thing? It's a magnetar, one of the rarest and most extreme types of neutron stars. Magnetars are already wild. They're born when massive stars collapse into dense cores just 12 miles across, but they spin slowly and have magnetic fields up to 1,000 trillion times stronger than Earth's. That's so powerful it could erase your credit card from halfway across the moon. But the hybrid star was even weirder. First of all, this magnetar was incredibly young. Based on how fast it was spinning down, losing energy, scientists calculated its age to be just 240 years old, making it the youngest magnetar ever discovered. That's practically a newborn in cosmic terms. And yet, even as a baby, it was already breaking the rules. It spun once every 1.36 seconds, which is very fast for a magnetar, since most take several seconds to complete a single rotation. But here's where things get really strange. The hybrid star also started emitting radio waves, something only a few magnetars have ever been seen doing. See, normal neutron stars that emit radio waves are called pulsars. Magnetars usually don't act like pulsars because their magnetism interferes with the beam mechanism. But the hybrid star did both. It had the magnetic fury of a magnetar and the precise radio pulse of a classic pulsar. This strange mix gave astronomers a once-in-a-generation opportunity to study a dual-nature object. One team even compared it to finding a tiger that purrs like a house cat but roars like a lion. It wasn't just odd, though. It was also dangerous. During the time of finding, the hybrid star sent out strong X-ray bursts as its magnetic field bent and snapped like a rubber band under stress. This is how magnetars usually act. When the field lines move around, they send out bursts of very high-energy radiation. We learned something important from those bursts. Using the NICER telescope aboard the International Space Station and the XMM Newton X-ray Observatory, scientists were able to measure the surface temperature, emission profile, and spin behavior of the object. The temperature was about 10 million Kelvin. That's over 1,700 times hotter than the surface of the Sun. Over the following weeks, the hybrid star dimmed rapidly in X-rays. But unlike most magnetars, its radio signals persisted. In fact, those radio pulses even began to drift in frequency and shape, hinting at complex changes in the star's magnetic field. Another reason is that this thing is close to what we call the pulsar death line. In the study of neutron stars, that's the point at which the star's energy drops too low to make radio waves. But the hybrid star could be moving back and forth across that line, sometimes living and sometimes dead. It could be the missing link in the history of how magnetars and pulsars evolved. A few months after its discovery, the star began to behave more like a traditional magnetar again. It stopped pulsing clearly in the radio, and its X-ray emissions began to stabilize. This shift in behavior suggests the magnetic field is reconfiguring itself, like the internal wires of a broken machine trying to find a new circuit. The hybrid star is still a secret, as of right now. Several people think it's a magnetar that could become a radio pulsar with a long lifespan, or it could burn out and disappear totally. About 16,000 light-years away, it is close to the galactic plane, which is where many big stars are born and die. That makes it a great place to study young, very cold star bodies. GRB 090423, the Ancient Flash. On April 23, 2009, telescopes caught a brief but blazing flash of gamma rays that came from 13.1 billion light-years away. It was named the Ancient Flash, and even though the burst itself lasted less than 10 seconds, it had already traveled for over 90% of the entire age of the universe before reaching Earth. This wasn't just any gamma-ray burst. This was, and still is, one of the oldest and most distant explosions ever observed. The light from the Ancient Flash began its journey just 630 million years after the Big Bang. That means it erupted when the universe was still in its cosmic toddler phase, a time before galaxies were fully formed, before heavy elements were common, and before the first generation of stars had even fully lived and died. What exactly did we see? The ancient flash is thought to be the death of a very large star that collapsed into a black hole. This star is at least 30 times the mass of our Sun. Just that doesn't come as a surprise. Most gamma-ray bursts that last a long time are caused by these crashes. This event is unique because it happened so early in the history of the universe. It gives us a clear view into the cosmic dark ages, a time when most telescopes can only guess what was going on. When a star that massive collapses, it doesn't just go quietly. It sends out powerful jets of gamma radiation, moving at nearly the speed of light. These jets pierce through the dying star's outer layers and shine for only a few seconds, but they are among the brightest signals in the entire cosmos. Thanks to NASA's SWIFT satellite, which detected the initial burst, astronomers around the world quickly aimed their telescopes at the source. What they found stunned them. The light had been redshifted to such an extreme degree that its signature lines had been stretched by the expansion of the universe more than ever recorded in a GRB. That redshift was measured at z equals 8.2, breaking previous records. To understand how big that is, redshift tells us how much the universe has expanded since the light left its source. A redshift of 8.2 means the universe was 9 times smaller back then. Earth didn't exist. The Sun hadn't been born. Even the Milky Way was just starting to come together. So how did a massive star, one capable of a gamma-ray burst, exist in such a young universe? At that time, the cosmos had just begun forming population 2 stars, which are old stars made mostly of hydrogen and helium, with very few heavier elements. The first generation, population 3 stars, were even more extreme. Huge, hot, and short-lived, and likely responsible for ionizing the early universe. While we haven't seen a confirmed population 3 star yet, the ancient flash might be the closest evidence we've ever had that one of their descendants blew itself apart. Its brightness also told us something profound. Even in a universe that was still assembling itself, massive stars were forming, living fast and dying violently. And because gamma-ray bursts are detectable from across the entire visible universe, they've become one of our best tools for probing the early universe, like flashbulbs going off in the darkness of deep time. Not only was the ancient flash far away, it was also very active. In just a few seconds, the burst released more energy than our Sun will make in its full 10 billion year life. Still, the only reason we were able to catch it was because its jet was pointing straight at Earth. We would not have seen it at all if it had been tilted even a little. This would have made us less knowledgeable about our own cosmic past. Finding the ancient flash actually led to a whole new generation of gamma-ray burst hunters, such as NASA's James Webb Space Telescope, which is now actively looking for signs from similar very far-away objects. It would be helpful to find another one like this, or even something even older. It would help us figure out how galaxies formed in the beginning, how black holes grew, and what the first stars were really like. Even today, 15 years after its detection, the ancient flash remains a cosmic milestone. It pushed the limits of what we can observe and proved that the universe had already matured enough to create powerful, massive stars and destroy them when it was just a few 100 million years old. SN 1054/Crab Nebula, the daylight supernova. Picture getting outside one morning and seeing a brand new star that is so bright you can see it during the day. That's exactly what took place in 1054 AD, almost 1,000 years ago. Native American rock paintings, Chinese scientists, and Japanese monks all wrote about a blinding point of light that showed up in the sky and stayed there for over 23 days during the day and almost 2 years at night. That event in space is now known as SN 1054 and can still be seen in the sky as the Crab Nebula. This wasn't just any supernova. SN 1054 is one of the most extreme and scientifically important stellar explosions ever witnessed by humans, because we saw it with our naked eyes long before telescopes existed. And what's left behind, the Crab Nebula, is one of the most studied objects in all of astronomy. SN 1054 is classified today as a Type II supernova, the death of a massive star that ran out of nuclear fuel. Without fusion to hold it up, the star's core collapsed under gravity, forming an ultra-dense neutron star, while the outer layers were blown into space at millions of kilometers per hour. But this particular star wasn't quietly tucked away in a dark part of the sky. It exploded in the Taurus constellation, and its position made it easy to spot from Earth. Chinese court astronomers described it as a guest star that appeared on July 4, 1054, and outshone every other star in the sky, even visible during the midday sun. To be visible in daylight, the explosion had to be absolutely massive, likely shining with the brightness of a full moon. That means the supernova was tens of millions of times brighter than the sun for weeks on end. The remnant of that explosion is what we now call the Crab Nebula, or M1 in the Messier catalogue. Located about 6,500 light-years away, the Crab is a twisted, glowing web of hot gas and energetic particles, expanding at over 1,500 kilometers per second. It's still growing, nearly a millennium later, like a cosmic scar slowly stretching outward. But the centerpiece of the nebula, the heart of this story, is the Crab pulsar. That's the leftover core of the original star, a neutron star just 20 kilometers wide, spinning 30 times per second and emitting beams of radio waves, X-rays, and gamma rays like a lighthouse on fire. This object is one of the most powerful known natural particle accelerators in the universe. The Crab pulsar shoots out electrons and positrons so fast that they reach energies of trillions of electron volts, far beyond anything we can do on Earth. The pulsar also pulses across the entire electromagnetic spectrum, from low-frequency radio all the way up to deadly gamma rays. It's a spinning beacon of death, powered by rotational energy and intense magnetic fields. What makes the Crab Nebula extra unusual is how steady its emissions are. Over time, most nebulae cool down and go away. But the Crab is like a cosmic generator. It's always bright and busy, like it's stuck in overdrive. This has turned it into a calibration tool for modern observatories. When scientists want to check if their telescopes are working properly, especially gamma-ray and X-ray detectors, they often point them at the Crab Nebula. It's become so reliable that astronomers even joke, if you don't see the Crab, something's broken. In 2011, the Crab pulsar surprised everyone again by producing a sudden gamma-ray flare. That spike in brightness happened in just a few hours, which means something changed very quickly inside, or around the pulsar. This flare released 400 times more energy than the sun emits in a second, all packed into high-energy gamma radiation, and we still don't fully understand. SN 1054 wasn't just a supernova. We saw it with our own eyes, without any fancy equipment. It left behind a piece that is now used as a particle collider, a laboratory for high-energy physics, and a lighthouse to help people learn about neutron stars. Its pulsar is still spinning after almost 1,000 years, giving energy to a cloud that looks like it just blew up. All of this came from a star that died 6,500 years ago. Its light finally reached Earth in 1054, just as people were beginning to look up. Maxi J 1820 plus 070, the jet gun. Because space is so quiet, black holes are often thought of as silent eaters that take in matter, hide it all behind their event horizon, and never make a sound. But some black holes aren't shy. Some of them spit, some of them take off, and one of them, Maxi J 1820 plus 070, shot matter jets at speeds close to 80% the speed of light, making it look like a cosmic machine gun. Astronomers called it the jet gun because of this. The jet gun is a stellar mass black hole, discovered in March 2018 by the Japanese Maxi, monitor of all sky X-ray image instrument aboard the International Space Station. At first, it looked like a typical low-mass X-ray binary, a black hole paired with a normal star, slowly stealing material from its companion. That stolen gas forms a hot accretion disk around the black hole, glowing in X-rays and occasionally erupting in outbursts. But this one didn't just flare. It erupted both in X-rays and in the radio spectrum, signaling something was shooting out. That something turned out to be relativistic jets, tightly focused beams of particles blasting out of the system at near light speeds. As matter spiraled inward toward the black hole, friction in the accretion disk superheated the gas to millions of degrees. When the disk became unstable, a burst of X-rays signaled that a huge amount of material was falling inward. But instead of all of it vanishing into the black hole, Some of that matter was redirected by twisted magnetic fields and launched outward, like a slingshot, along the black hole's spin axis. The jet's speed and clarity made this event stand out. Astronomers were able to get a good look at the released jets by using very long baseline interferometry, VLB1, a method that uses radio telescopes all over the Earth to work together like a big dish. They saw the jets moving at 0.8 times the speed of light and watched as they split apart over time. This gave us a clear picture of how the explosion was shaped. That wasn't just theory, it was real, moving proof that a black hole was throwing matter out into space right now. Now, black holes don't have physical surfaces to push off from, so how are they launching jets? The likely answer is something called the Blandford-Znajek process. In this model, powerful magnetic fields anchored in the spinning accretion disk tap into the rotational energy of the black hole itself. Like pulling juice from a spinning flywheel, these fields extract energy and use it to launch plasma into space at insane speeds. The jet gun gave us some of the clearest observational evidence that this process is real and happening in our own galaxy. What's even more fascinating, the jets were not symmetrical. One jet appeared to be moving faster than the other, but that's an illusion caused by relativistic beaming. The jet moving toward us appears faster and brighter because its light is compressed by its motion. The one moving away is dimmed. This let astronomers confirm just how close to light speed the ejection was, offering a rare 3D glimpse into jet dynamics. Further observations with the NICER telescope on the ISS revealed X-ray echoes, reflections of the blast bouncing off the gas around the black hole. These echoes showed changes in the inner accretion disk, which shrank and re-expanded during the outburst. It was like watching a storm explode in a cosmic whirlpool, then watching the whirlpool heal itself, but with relativistic physics. The energy involved? Enormous. The jets carried away a significant fraction of the black hole's accreted mass, converting it into kinetic energy on a galactic scale. That's like launching billions of nuclear bombs every second, only focused into a beam a few kilometers wide. The jet gun has only 10 times the sun's mass. Even though it's not as heavy as a giant black hole, it can fire jets as powerfully as quasars and active galaxies billions of light years away. Scientists also had a unique chance to look into how black holes grow and control themselves during the event. The accretion ring may stay cool thanks to jets like these, which can also carve out gas or even stop future feeds by blasting away the fuel that is available. One reason some black holes stay stable and others turn into monsters could be this kind of feedback. The jet gun wasn't the biggest or hottest star, but it was one of the fastest jet launchers ever seen in our own Milky Way. It also gave scientists a new way to look at the physics of extreme ejection. Not only did it eat matter, but it also turned around and shot it back out into space like a gun. GRB 130427A, the eternal afterglow. On April 27, 2013, a gamma-ray burst lit up the universe in a way we had never seen before. Not because it was short and intense, but because it was long, powerful, and refused to fade. This cosmic blast, named GRB 130427A, became one of the most energetic gamma-ray events ever recorded, and left behind an afterglow that seemed to burn forever. As the time struck 0747 UTC, satellites all over the solar system went into alert. A huge burst of very high-energy gamma rays from the constellation Leo, which is about 3.6 billion light-years away, was picked up by NASA's Fermi Gamma Ray Space Telescope, the Swift Observatory, and even telescopes on the ground. In terms of gamma-ray bursts, that's pretty close. You'd be right next to one of the most powerful blasts in the universe. The eternal afterglow lasted for about 20 seconds, which definitely makes it a long GRB. These are the kinds of events that happen when a huge star falls apart and turns into a black hole. It wasn't like any other burst, though. Gamma-ray photons with energies of up to 95 billion electron volts, GeV, were caught by the Fermi sensor. That's more than 35 billion times stronger than light that we can see. The most powerful particle accelerator on Earth, the Large Hadron Collider, maxes out at about 13 TeV. This burst casually beat that, and did so from 3.6 billion light-years away. One photon was so energetic that scientists at Fermi had to double-check whether their instruments were malfunctioning. They weren't. But the real twist came after the burst. Most gamma-ray bursts die out quickly. Within a few hours or days, they fade into nothing. But the eternal afterglow refused to die. Its X-ray afterglow remained visible for weeks. Its optical light was so bright that amateur telescopes on Earth picked it up. And its gamma-ray emission continued for over 20 hours, longer than any GRB we've ever observed at such high energy. With so many observatories tracking it, from NASA's Nuster and Swift to ESA's Integral to ground-based telescopes in Chile and the Canary Islands, we were able to watch every stage of the burst's evolution. We saw the shockwave plowing through space, the jet structure unfolding, and the magnetic fields rearranging as energy was drained from the system. The best current model says the eternal afterglow came from a Wolf-Rayet star, a massive, hot star stripped of its outer hydrogen layers, teetering on the edge of collapse. When its core caved in, it formed a black hole, which in turn triggered two ultra-relativistic jets of plasma. These jets pierced through the collapsing star and shot into interstellar space, giving off gamma rays as they blasted outward at nearly the speed of light. It wasn't just the energy that made this event so extreme, though. It was how long the energy lasted. Scientists thought that the high-energy photons would quickly disappear because they would be spread out by the gas around them or weakened by the distance. Instead, they kept coming over and over again. The gamma rays from the eternal afterglow didn't just go away, they got weaker over time and stayed strong for hours. We learned that the jet was very stable and had very little internal scattering. This meant it was likely cleaner, faster, and more focused than any other burst jet we had seen. Scientists used the afterglow data to look into the strength of the magnetic field, the speeding up of electrons, and even parts of quantum gravity theories. For example, they wanted to see if space-time at high energies slows down the arrival of photons. It was found that there was no delay, which sets new bounds on strange physics models. Even though the burst happened very far away, it was so bright that if it had happened in our galaxy, it would have blinded satellites, maybe messed up communications, and even left a glow in Earth's atmosphere that we could see. It was so strong that we could see it from space, but it was close enough to tell us that these things could happen anywhere at any time. The eternal afterglow rewrote the playbook on gamma-ray bursts. It showed that bursts could be long-lived, ultra-energetic, and observable across the entire electromagnetic spectrum, all at once. For years after the event, its afterglow remained a reference point for every new burst, a sort of yardstick for cosmic explosions. PSR J0952-0607, the cosmic blender. It can take days or even years for most stars to make one full turn. Neutron stars, which are the very dense remains of dead stars, turn around once every few seconds or so. Then there's PSR J0952-0607. This neutron star isn't like any other. At an amazing 707 times per second, this pulsar spins faster than any other known pulsar in the universe. This thing is spinning so fast that the surface is moving at about a fifth the speed of light. It is only 20 kilometers wide. Scientists called it the cosmic blender because of this. And when we say blender, we mean it in the most extreme way that goes against the laws of physics. The outer centrifugal force would actually tear it apart if it spun much faster. How does something like this take place? We need to look back at how pulsars form to understand that. Node stars that are pulsars have very strong magnetic fields. From their magnetic poles, they send out beams of radiation. As they spin, these beams pass by Earth like lighthouse signals, and that's what we call pulses. Most pulsars start off with fast spins after the supernova explosion, but over time, they slow down as they lose energy. However, there's a trick to revving one back up: binary interaction. The cosmic blender lives in a binary system, meaning it has a companion star. Over billions of years, that companion dumped gas onto the neutron star in a process called accretion. This swirling material didn't just feed the pulsar, it acted like a cosmic wrench, spinning it up faster and faster, turning it into a millisecond pulsar. This particular pulsar was discovered in 2017 using LOFAR, Low Frequency Array, a powerful network of radio telescopes across Europe. But what made it truly special wasn't found until 2022, when scientists used the Keck Observatory in Hawaii to observe the faint, flickering light from its dying companion. That's how they were finally able to confirm the spin rate. A record-breaking 707 revolutions per second, the pulsar's companion star is barely there. It's a shriveled remnant of what used to be a normal star, now weighing less than 5% the mass of our Sun. It's been so thoroughly cooked, eroded, and blasted by radiation from the pulsar that astronomers call these companions black widow stars, after the spider that eats its mate. The pulsar is essentially vaporizing its partner. That intense radiation, a mix of X-rays, gamma rays, and charged particles, is slowly stripping away what little remains of the companion, possibly erasing it completely in a few 100 million years. It's not just a binary system, it's a slow-motion execution. The cosmic blender is also a test bed for extreme physics. At that rotation rate, the neutron star's structure is under enormous strain. It must maintain a perfect balance between gravity pulling inward and centrifugal force pulling outward. If it spun just a few % faster, theory says it would fly apart, scattering its contents into space. So this pulsar is sitting right at the edge of what's physically possible. This makes it a natural laboratory for testing the equation of state, the rules that determine how matter behaves at nuclear densities. We can't build neutron stars on Earth, but by watching how close this one is to the spin limit, we get clues about what kind of exotic particles or quark matter might exist inside. It is also important for studying gravity waves in space. What if this pulsar's surface has even the smallest bump or wobble? It should send out tiny gravitational waves, which are like ripples in space-time. We still haven't picked up those waves from the cosmic blender, but it's still one of the best places to do future tests with more sensitive tools like LISA or the Einstein telescope. It's about 3,200 light-years away, so the sounds we can pick up now were actually sent out during the dark ages of human history, long before the Renaissance, the printing press, and recorded music. Each time it pulses, it's like getting a word from the beginning of time. Swift J 1644 plus 57, the zombie star. A lot of stars stay dead after they die. They could end up as a neutron star or black hole, or they could explode as a supernova and fade into the background of the universe. But Swift J 1644 plus 57 wouldn't do what was asked of it. It died, but it kept coming back, once more, and it exploded over and over again in a way that no one had ever seen before. Astronomers called it the zombie star because of this. The story begins on March 28, 2011, when NASA's Swift Observatory picked up a powerful X-ray flare coming from the direction of a galaxy 3.8 billion light-years away. At first, astronomers thought it was just another gamma-ray burst, a big flash, some fading light, and done. But this one didn't fade. Instead, the object began emitting bright, sustained X-ray and gamma-ray radiation, not just for minutes or hours, but for days. It flared, paused, then flared again, stronger than before. Then it blasted out radiation again. This cycle repeated for months, with variations in brightness that suggested something was happening deep in the heart of that distant galaxy, something alive, at least in a cosmic sense. What did it mean? They found the answer when they looked more closely at the center of the galaxy. The flare wasn't from a supernova or a neutron star that went off on its own. It came from where the galaxy's center black hole is. Not just any black hole either, a very big black hole that probably weighs 1 million times as much as the Sun. It wasn't a dead star having a temper fit. A black hole ate a star while it was still alive. This is called a tidal disruption event, TDE. That means the following. A star got too close to the black hole at the center of the galaxy. The star was ripped apart by the strong tidal forces, which are the difference in gravity pull between the star's near and far sides. It wasn't just sucked up by the black hole, it was torn apart like paper going through a cosmic shredder. But in this case, the debris didn't fall all at once. Instead, it spiraled into an accretion disk, a swirling funnel of gas and stellar guts, feeding the black hole bit by bit. And in a rare twist, the black hole launched a jet of material directly at Earth, allowing us to observe the entire feeding frenzy in real time. This made the zombie star the first confirmed TDE with a relativistic jet and one of the most extreme cases of black hole reanimation ever recorded. The light curve, the graph showing its brightness over time, didn't follow any known patterns. It rose, dipped, rose again, dropped violently, and continued flashing like a cosmic strobe light. These variations weren't random. They hinted at clumps of stellar debris being dragged into the black hole at uneven intervals, like watching a slow-motion horror movie where each frame is a fresh meal. The event lasted for over a year, much longer than any gamma-ray burst. Normally, jets from black holes die off quickly once the fuel is gone, but this black hole kept eating, kept flaring, kept shooting out beams of energy like it just couldn't stop. It was behaving like a zombie, a dead thing still active, still dangerous, and still very, very hungry. Multi-wavelength observations, from radio to X-rays, confirmed the event's bizarre nature. Radio telescopes tracked the jet's expansion, showing that it moved at 99.5% the speed of light. Meanwhile, X-ray telescopes like Chandra and XMM Newton revealed the inner disk's chaotic heating and cooling, suggesting violent shocks and magnetic reconnections were taking place. The zombie star is still being studied after all these years. The newest models show that the black hole spun very fast, which let it hold strong magnetic fields that sent the energy into focused jets. The spin may have even been the reason why the TDE didn't just go away. It turned a normal meal into a long show of damage. Some scientists think the zombie star might be just the tip of the iceberg. They think that other black holes may do this all the time, but we miss them because the jet isn't aimed at Earth. It's up to you whether you think we were lucky or not. A huge black hole woke up in a faraway galaxy, ate a star, and screamed about it at us through a cosmic speaker. Assassin 15 LH, the supernova impostor. Astronomers thought they were seeing just another supernova when they saw ASASSN 15LH for the first time in June 2015. A supernova is the explosion death of a huge star. This one, though, wouldn't follow the rules. It was too bright, too active, and too strange to be a regular death of a star. It was so strange that it quickly got the name the supernova impostor. First, let's talk about the crazy numbers. The supernova impostor, which is pronounced Assassin 15LH, was the biggest event that looked like a supernova that has ever been seen. As bright as it got, it was more than 500 billion times brighter than the Sun, which is more than 20 times brighter than the whole Milky Way galaxy. Yes, that is a true statement. This one item shone brighter than all 100 billion stars put together for a few weeks. Astronomers using the All-Sky Automated Survey for Supernovae, ASASSN, were the first to detect it. It came from a galaxy 3.8 billion light-years away, and initially it was classified as a superluminous supernova SLSN, a relatively new category for explosions that are 10 to 100 times brighter than normal supernova. But as scientists began studying it more carefully, things didn't line up. First, the host galaxy was wrong. Most superluminous supernovae happen in small star-forming dwarf galaxies. The supernova impostor came from a large, old and passive galaxy, the kind where stars have mostly stopped forming. That alone raised eyebrows. Second, the spectrum didn't match. Most SLSNA show strong hydrogen or oxygen features in their light, the fingerprints of the elements involved in the explosion. The supernova impostor showed none of these, and the temperature of the explosion was too high to explain with standard models. Third, it brightened twice. After its initial record-breaking peak, the supernova impostor began to fade, as expected. But then, 2 months later, it brightened again. This re-brightening was completely unexpected. Supernovae don't do that. Once they peak, they fall off, and that's it. The supernova impostor was clearly something else. So if it wasn't a typical supernova, what was it? One leading theory is that the supernova impostor was powered by a magnetar, an extremely magnetic neutron star formed in the explosion. In this model, the newborn magnetar spins rapidly, hundreds of times per second, generating enormous magnetic fields that inject energy back into the explosion, keeping it hot and bright for longer. This could explain both the luminosity and the double peak. But there's a catch. For a magnetar to power the supernova impostor, the neutron star would have to spin faster than any magnetar ever measured, and its magnetic field would have to be so strong that it would almost break the rules of physics. That's not impossible, but it seems odd. A tidal disruption event, TDE, could be the supernova impostor. This is when a supermassive black hole rips a star apart. If that's true, then this wasn't even a supernova. It was a feeding event where a black hole ate a star and lit up the galaxy in the process. The explosion happened very close to the center of its host galaxy, exactly where a supermassive black hole would be. That location lines up with typical TDAs. But again, the spectrum and light curve don't quite fit. It's like the event is half one thing, half another, fitting into neither box cleanly. That's why the supernova impostor became the supernova impostor. It looks like a supernova from far away, but up close it's too weird to pin down. Follow-up observations with Hubble and Chandra helped rule out some possibilities, including interaction with surrounding material, which would have shown signs of shock-heated gas. There were no signs of dust, no radio emissions, no normal fingerprints of stellar explosion aftermath, just blinding, sterile light. After the rebrightening, the supernova impostor faded again and never came back. It left astronomers with a pile of data, a dozen conflicting models, and no clear answers. It remains to this day a one-of-a-kind mystery. No other explosion has matched its brightness, profile, or bizarre behavior. PSRB 1509-58, The Hand of God. A bright cloud of gas and radiation sits 17,000 light-years away in the southern sky. It looks unsettlingly like a big hand reaching into space. It's true, it's very big, and right in the middle of it is PSRB 1509-58, one of the strongest neutron stars ever seen. This is the pulsar that many scientists now call the Hand of God. This is not just a cute name. NASA's Chandra X-ray Observatory took a picture of the structure using high-energy X-rays. The picture showed a 150 light-year wide glowing nebula. The shape looks like a hand, with fingers, a palm, and even a wrist. It's like a holy hand was frozen in the middle of reaching across the universe. This isn't art, though. It's the study of space, astrophysics that is violent, intense, and amazing. At the core of this structure lies the Hand of God, a 33-millisecond pulsar, a rapidly spinning neutron star that completes a full rotation 30 times per second. This object formed from the collapsed core of a supernova explosion roughly 1,700 years ago, based on the expansion rate of the surrounding gas. Since then, it's been spinning like a cosmic engine, pouring energy into the space around it. What makes a star, even a neutron star, make something that looks like a hand? There are bands of particles and electromagnetic energy, mostly X-rays, coming from the pulsar as it spins. A pulsar wind nebula is the name for the cloud of charged particles that these beams shine on. It's like a beacon beam going through fog. You can't see the beam itself, but you can see the light it casts on the fog. In this case, though, the mist is moving at relativistic speeds, and the lighthouse is a neutron star whose magnetic field is 1 trillion times greater than Earth's. As a result, spindly, rough waves of matter and light that are made by magnetic fields and lit up by particles that are almost moving at the speed of light. That's what gives the so-called Hand of God its fingers and palm. It's just an optical effect caused by powerful physics, but it looks eerily like a person. PSRB 1509-58 isn't just putting on a light show, it's pumping out energy at a phenomenal rate. This pulsar loses about 7% of its rotational energy every year, which is absurdly fast. That energy doesn't disappear. It gets dumped into the surrounding nebula, energizing the magnetic fields and accelerating particles. The speed of this decay means the pulsar is still in its youthful phase, energetically spinning down from its original birth speed. In fact, the Hand of God is one of the youngest known pulsars that we've detected with this level of clarity. That makes it an important benchmark for studying how neutron stars evolve in their early stages. Scientists have used this system to test all sorts of high-energy physics theories, including how pulsar wind termination shocks work. That's where the high-speed wind from the pulsar slams into surrounding gas, creating a sort of standing shockwave that glows in X-rays and gamma rays. Studying this helps us understand everything from supernova feedback in galaxies to how cosmic rays get accelerated. There's even speculation that the structure might not be entirely symmetrical. Some researchers believe that the hand shape could be formed partly by instabilities in the magnetic field, or asymmetric ejections of material from the initial explosion. The fingers might be regions where matter is more dense or more excited, glowing brighter as the pulsar's energy hits them head-on. So while it looks like a divine gesture frozen in space, what you're really seeing is a shockwave of high-energy particles shaped by invisible magnetic scaffolding, animated by a pulsar that's spinning down to its death very, very slowly. What way does the hand point? It is roughly lined up with another supernova residue farther away, which is why some people call that area the arm of God. Even though there isn't a known physical link, the alignment is so creepy that it made the news. At the middle of it all is a dead body, the core of a star that used to be alive but has since been crushed. It painted a building so scary that it became a sign of divine power or a divine warning, depending on how you look at it. IGRJ 17091-3624, the black hole heartbeat. People often think of black holes as scary, quiet monsters that are dark, hungry, and lack rhythm. But in the constellation Scorpius, about 16,000 light-years away, there is a black hole that does the unthinkable. It beats over and over again, like a beating in space. Its name is IGRJ 17091-3624, and scientists call its strange behavior the black hole heartbeat, because it seems so alive and regular. The black hole heartbeat is a black hole with the mass of a star and is part of a pair. A bright accretion ring forms around it as it pulls matter from a nearby star. It wasn't just how bright this black hole was that made it famous, though. It was how its brightness changed over time. In 2011, observations from NASA's Rossi X-ray Timing Explorer (RXTE) revealed that this black hole wasn't static. It was producing quasi-periodic X-ray oscillations, pulses of X-ray light that rose and fell in a distinct pattern, repeating every few seconds. This kind of pattern had only been seen before in one other place, the infamous black hole system, the Greedy Eater, which is known for its complex variability and chaotic looping light curves. But the black hole heartbeat was different. It showed a strange heartbeat pattern, just like the famous black hole GRS 1915. In this mode, the X-ray light from the black hole rises and falls in a steady rhythm, almost like it's breathing. What's really happening is a repeated cycle. Gas builds up in the inner disk, heats up, collapses inward, and then bursts outward again. It's a kind of pulsing motion as the black hole feeds on its surroundings. This heartbeat is caused by something called accretion disk instability. In simple terms, here's how it works. The black hole pulls in gas from a nearby star. That gas spirals into a disk and heats up due to friction. When the pressure and temperature get too high, the inner part of the disk collapses suddenly, dumping a huge amount of gas into the black hole. Then the disk cools, empties out, and the whole process starts again, over and over, like a cosmic heartbeat. Every pulse you see is a mini explosion of energy, releasing X-rays as the black hole inhales another gulp of matter. This happens every few seconds, over and over, sometimes for hours. It's one of the most predictable and mesmerizing patterns we've ever seen in a black hole system. The black hole heartbeat is very light. GRS 1915 is thought to be about 12 to 14 solar masses, but IGRJ 17091 is only thought to be about 8 solar masses, but it acts almost the same. In other words, the heartbeat isn't just about mass. It's also about how close the accretion disk is to the event horizon and how the gas behaves under strong magnetic and gravitational fields. Even though they both show the same colors, IGRJ 17091 is not as bright as GRS 1915. It's possible that IGRJ 17091 is located over 20,000 light-years away, which is a lot farther away than was first thought. Its accretion disk is also at a different angle, which means we see less of the high-energy release. Researchers also noticed other weird patterns beyond the heartbeat: flickers, dips, spikes, and loops in the light curve that resemble behavior seen in lab plasma experiments and supercomputer simulations of fluid instabilities. It's like the black hole has multiple modes of variability, switching between them as conditions change in its disk, a kind of cosmic rhythm disorder. The size of these bursts is what blows my mind the most. Imagine something only a few kilometers wide, smaller than a city, emitting more energy in a few seconds than the whole planet would use in 1,000,000 years. Now picture it doing that over and over again every few seconds with only gravity, pressure, and magnetism controlling it. The black hole heartbeat doesn't just make us think about what we think black holes are like. Somehow, it makes them seem more like people. It helps them keep time, a beat, a circle. The deep gravity rhythm that beats out energy seems like the breath of the universe itself. It happened before life, sound, or language. OGL 2016 BLG 1928, the Phantom Planet. It blinked. For just 42 minutes, a tiny flicker of light passed through a telescope's view in 2016. No flash, no glow, no lingering signal. Just a short, sharp dip in starlight. But that flicker told a story more mysterious than any star explosion or black hole outburst. It revealed something truly rare. An Earth-mass rogue planet drifting freely through the galaxy, completely unbound to any star. Astronomers named the event OGLE 2016, BLG 1928, but they called the object behind it something far more dramatic: the Phantom Planet. Why phantom? Because it has no star, no solar system, no orbit that we can trace. It wanders alone through the Milky Way, invisible, cold, and nearly undetectable. This is one of the smallest and loneliest objects ever discovered by gravitational microlensing. OGL stands for the Optical Gravitational Lensing Experiment, a long-running survey that watches millions of stars across the sky, mostly toward the center of our galaxy. Its goal is to catch microlensing events, rare moments when a massive object passes in front of a distant star and bends its light like a magnifying glass in space. The thing that is lensing doesn't have to give off light. In fact, you can't always see it. For this reason, there are rogue planets, also known as free-floating worlds. When a planet moves between us and a faraway star, it can temporarily make the star appear bigger. We only see the star briefly getting brighter and then getting darker. In June 2016, OGL picked up such an event. A distant star in the galactic bulge brightened and dimmed in a perfect symmetrical curve, the telltale shape of gravitational lensing. But the entire event lasted just 42 minutes. That's incredibly short. And it told scientists something big. The lensing object had to be tiny, far smaller than a star, or even a brown dwarf. Astronomers carefully modeled the object and came to the conclusion that it was most likely a planet about the mass of Earth. Here's the catch. It wasn't orbiting anything else. It wasn't close to a host star, and the data didn't show any stars. It was just outside, by yourself. This changed everything. A planet passes in front of its star, which is called a transit, and the star wobbles because of the planet's gravity. These are the main ways we find exoplanets. But those ways need a big star. A rogue planet like the Phantom Planet doesn't have one, so the only way we can find them is through microlensing. Scientists thought that rogue planets might exist before this event. They thought that these planets might have been thrown out of their home systems by chaotic gravitational forces or collisions early in their formation. But the Phantom Planet showed that planets about the size of Earth could live for billions of years in deep space, where they would be unseen and cold. They may be shockingly common as well. Based on some computer models, the Milky Way might have billions of rogue planets, which is more than there are stars. A lot of them will never be seen. They're not bright. Light doesn't bounce off of them. They're just clumps of rock, ice, or gas moving around in the dark forever. The Phantom Planet was just lucky. It passed in front of a star in the background while we were watching. Also, let's not forget about what this means for life. Could a bad world hold it up? Maybe even surprisingly. Even without a star, a planet could stay warm if it had a thick atmosphere, nuclear core heat, or an ocean below the surface. Geothermal energy could keep life going on in a world that isn't supposed to be there, even if it's dark and under ice. Even though the phantom planet wasn't always livable, it made us think about a whole new group of worlds where life could hide. Microlensing scans that are even more powerful, like the one that NASA is building to look at the Romans, should find dozens or even hundreds of these kinds of events. With each flicker, a different ghostly figure could be seen, another dark visitor floating between the stars, soundless and invisible until gravity lets it down for a moment. GRS 1915 plus 105, the Greedy Eater. GRS 1915 plus 105 would be a messy, chaotic glutton if black holes could have personalities. It would eat matter faster than it can handle, spit it out, and start the cycle all over again, causing cosmic indigestion. Astronomers have called it the Greedy Eater for a long time because of this, and it has earned that name very well. The Greedy Eater is a stellar mass black hole located about 36,000 light-years away in the constellation Aquila. It was discovered in 1992 by the Granite Space Observatory, and from the beginning, it stood out. Not because of how quiet or subtle it was, but because it was too bright, too active, and too unpredictable. At the time of its discovery, it was the most luminous X-ray binary ever observed in our galaxy. But its behavior was unlike anything scientists had ever seen. Instead of a steady stream of radiation, the Greedy Eater produced wild oscillations. Its X-ray brightness would rise and fall erratically, sometimes flashing like a strobe light, sometimes dropping completely in seconds, only to flare again just moments later. Why? Because this black hole doesn't just eat, it binge eats and then vomits jets of matter when it can't keep up. The Greedy Eater is in a binary system, paired with a normal star about 1.2 times the mass of the Sun. The black hole pulls gas from this star into a swirling accretion disk, but instead of calmly feeding on the gas, the Greedy Eater exhibits extreme variability, cycling between feeding and ejecting at dizzying speeds. This cycling takes place in so many different ways that scientists had to name them with Greek letters, like the Rho class, the Mu class, the Kappa class, and so on. Bursts, dips, loops, and beats make up the melody of each class. It can repeat every few seconds or every few minutes. The black hole's most famous state is the heartbeat state, in which its inner disk falls apart and then rises back up again in a matter of seconds. The gas builds up near the event horizon until a certain point is reached. It then quickly falls in, sending out a huge amount of X-rays. When the disk is partly empty, the pressure drops and the cycle starts all over again. Seeing it is like seeing an unsteady breathing engine. During these eating events, this black hole sends out jets of matter. Astronomers have used radio devices like the VLA, Very Large Array, to see the Greedy Eater send out plasma blobs at speeds close to the speed of light. These jets go light years into space and cut holes in the material between the stars. It looks a lot like a micro-quasar, which are active galactic centers that can be seen in faraway galaxies, but are happening right here in our own neighborhood. And it's not just physics for the sake of curiosity. The Greedy Eater has become a laboratory for understanding how black holes feed, how jets form, and how accretion disks self-regulate under extreme gravity and magnetism. Its chaotic variability helped establish the idea of limit cycle behavior in accretion physics, a pattern where inflow and outflow continuously balance and break down over and over again. Interestingly, the mass of the Greedy Eater is unusually high for a stellar mass black hole, about 12.4 solar masses. That may not sound like much, but it makes it one of the most massive black holes formed from a single star collapse in our galaxy. That extra mass may contribute to its instability. The deeper the gravity well, the more violent the feeding. And something changed in 2018. The Greedy Eater went into a low-flux state and started to calm down. The once hungry eater looked like it was starving as its crazy cycles slowed down and the jets stopped moving. Some experts believe that the inner accretion disk may have disappeared or been messed up. Some people think the structure of the magnetic field fell apart. In any case, it stopped doing anything, like a monster taking a break. But the quiet didn't last all day. Small flares and X-ray bursts showed signs that the system might be starting up again by 2023. Nicer equipment on the International Space Station are still being used to keep an eye on it by astronomers who want to know if the greedy eater will return to its full glory of jet spewing and binge eating. PSRJ 17 19-1438b, the Diamond World. Astronomers found something so strange in 2011 that it sounded like something out of science fiction. A planet that might be mostly made of carbon crystals, or a big diamond. It circles a pulsar that spins very quickly about 4,000 light-years away in the constellation Serpens. They named it PSRJ 1719-1438b. Since then, people have called this strange world the Diamond World. This isn't a fancy diamond, so don't expect it to sparkle or shine. It looks more like something from another world than anything in our solar system. A millisecond pulsar, like PSRJ 1719-1438, is a type of neutron star that spins very quickly, more than 10,000 times per minute. Like a beacon, it sends out a beam of radio waves. Every time that beam crosses Earth, we pick up a pulse. It pulses 5,700 times per second, which makes it one of the things in the world that spins the fastest. That's already intense. But the real twist came when astronomers noticed a regular wobble in the timing of those pulses. That wobble meant something was tugging on the pulsar, a small companion object about the mass of Jupiter, but with an impossibly small radius of just 60,000 kilometers. That's smaller than Saturn, yet heavier than Jupiter. Something dense. Really dense. Here's the conclusion. The Diamond World is likely the core of a dead white dwarf star that has been stripped of nearly all its material by the pulsar. Over time, the intense gravity and radiation from the neutron star siphoned away the outer hydrogen and helium, leaving behind a tight, ultra-dense ball of mostly carbon and oxygen, compressed so thoroughly that the carbon crystallized. And what happens when carbon crystallizes under a lot of pressure? You get diamonds. It's not a sparkling gem. It's not clear, it's not cut, and it's not pretty. Astronomers think that the Diamond World might be up to 90% crystallized carbon based on its size, mass, and density. This tiny, dead, white-hot chunk of star matter could be the biggest diamond in the universe, since it has about the same mass as Jupiter and less space than Earth. It takes 2.2 hours for the planet to go around its pulsar, which is very close. It's so close that it only goes 600,000 kilometers above the neutron star's surface. That's about 1.5 times the distance between Earth and the Moon. But the system is so small that it could fit inside our Sun. It's a dance of death in space, with one dead star going around another, heavier body in a fast, endless waltz. What makes this system especially important is how it formed. Astronomers believe this is the end state of an ultra-compact X-ray binary, a system where one star evolves faster than the other, dies, and starts feeding on its partner. In this case, the neutron star devoured nearly everything its companion had, until all that remained was the degenerate carbon core. No atmosphere, no fusion, just crystallized pressure. It's a zombie world with a dead body circling a still pulsing heart. Why don't we have more of these? There are possibly dozens, hundreds, or even millions of these incredibly dense planetary remains out there. But it's hard to see them unless they're going around a pulsar. And we can't see the wobbles unless we're looking right at the beam of that pulsar. It's possible that diamond worlds are hard to find, or they could be hiding in plain sight, their dark shapes moving through space without being seen. Do you want to mine them? Don't bother. On the diamond world, the gravity would quickly turn a person into a paste. You would die right away from the strong radiation from the close pulsar, even if you were able to land on it. It's one of the least friendly places you can imagine. But as a cosmic curiosity, it's the only thing that compares. This is a world that started as a star. It lived, it burned, it died, and it was devoured, leaving behind a compressed core of near-pure carbon, orbiting its former partner in silence and darkness. XTEJ 1810-1977, the waking magnetar. It's quiet in most magnetars, not active. Space rocks are the dead bodies of stars that only sometimes scream into the universe with a burst of X-rays or a gamma-ray fit. But in 2003, something moved deep in the sign Sagittarius, and scientists saw a dead star wake up for the first time anywhere in history. The model number is XTEJ 1810-197. The waking magnetar is its name. It wasn't that it flared that made it so special. Magnetars do that sometimes. What happened afterward was what made it significant. A magnetar started to talk on the radio for the first time, turning on like a switch. This went against everything we thought these things should do. The waking magnetar was first identified in 2003 after a sudden burst of X-rays was picked up by the Rossi X-ray Timing Explorer (RXTE) satellite. Initially, it was just another transient, a one-off event that might fade into nothing. But follow-up studies showed the object was rotating every 5.54 seconds, consistent with the behavior of a magnetar, a highly magnetized neutron star. A few months later, in early 2004, a radio telescope detected something shocking, repeating radio pulses coming from the same location. Until that moment, magnetars had been known only as X-ray sources. They weren't supposed to produce radio pulses like normal pulses. The magnetic fields were thought to be too unstable. The surrounding space was too wild. It just wasn't possible. Still, there it was, a magnetar that had changed into a radio pulsar. It was proven that pulsars and magnetars are not different after this finding. The object was clearly a magnetar. It had a strong field and was the source of an X-ray burst, but it was acting like a pulsar. It was the first radio-loud magnetar that had ever been seen. Also, the radio waves weren't weak. They were very bright, polarized, and changed all the time. The pulses even had subpulses that moved around. This is a trait that is common in pulsars that are driven by rotation, but has never been seen in a magnetar before. It was such a thrill to find a tiger that could chirp like a bird. This sudden awakening raised a massive question. How many dead neutron stars are actually sleeping giants? Because if the waking magnetar could light up out of nowhere, that means other magnetars, or even other neutron stars we've marked as silent, might just be hibernating, waiting for some internal switch to flip. The radio pulses lasted until 2008, then suddenly stopped. For 10 years, the magnetar went quiet again. No pulses, no X-ray flares, no activity at all. Many thought the show was over. But in December 2018, it woke up again. Both X-ray and radio telescopes confirmed that the waking magnetar had restarted its activity. Its X-ray flux increased dramatically, and its radio pulses returned, though with different characteristics than before. The beam pattern had shifted, and the polarization changed. This showed something very important. Magnetars don't just switch between states once. They might do it more than once, changing from quiet to loud or from X-ray to radio, depending on changes in their internal magnetic or temperature fields. It's like the star has feelings, with times when it's quiet, times when it's angry, and times when it talks. It's not just a strange case, it's a prototype. After the waking magnetar, scientists found more radio-loud magnetars, such as PSR-J 1622-4950 and SGR-1935 plus 2154. SGR-1935 plus 2154 even sent out a fast radio burst, FRB, which is a mysterious, millisecond-long flash of radio energy that generally comes from a galaxy far, far away. One of the biggest puzzles in astronomy right now was solved when magnetars and FRBs were linked. In the beginning, the waking magnetar was the first to show that a magnetar could do more than just burst. We still don't know exactly what causes the transition. Some suspect it's due to magnetic crustal fractures, where the neutron star's outer layer cracks under stress, releasing energy and rearranging the magnetic field. Others think it's related to hotspots on the surface, heating up enough to generate coherent radio emission. VFTS 352, the star merger. Some stars don't last long and die young, but some people live so close to each other that their top layers touch, their cores twist around each other, and their fates are forever linked. About 160,000 light-years away, in the Tarantula Nebula in the Large Magellanic Cloud, lies VFTS 352, one of the craziest pairs of stars ever found. It is a contact binary that is so close that it breaks the rules of stellar physics. This isn't just a pair of stars orbiting each other, it's two massive stars that are literally fused at the surface, sharing their outer atmospheres and spinning toward an inevitable union. The star merger consists of two stars, each about 28 times the mass of the Sun, with surface temperatures reaching over 40,000 Kelvin. These are O-type stars, the most massive, luminous, and short-lived stellar class in the universe. These stars don't last long to begin with, and in this case they're speeding toward a much more violent fate. They orbit each other once every 1.12 days. Yes, daily. That means their centers are separated by less than 20 million kilometers, which is about half the distance from Mercury to the Sun. But because they're so huge, their outer layers overlap, forming a shared envelope of plasma. This configuration is called a contact binary, and the star merger is the most massive one of its kind ever observed, and it's barely holding together. Thanks to data from the Very Large Telescope, VLT in Chile, astronomers discovered that the two stars are in such close proximity that about 30% of their mass is shared in a common atmosphere. They are spinning so rapidly that the centrifugal force is almost counteracting gravity any faster, and the stars would literally break apart. So why does this matter? Because what happens next could create something the universe has never seen before. Either a colossal merged star or a pair of black holes locked in a deadly dance that ends with a cosmic collision. Let's look at the first possibility. The stars merge. As their outer layers continue to mix, they spiral closer and closer until their cores finally fuse into one enormous, rapidly spinning star, bigger than anything we've ever recorded. This supermassive star might end its life in a hypernova, a type of explosion far more powerful than a regular supernova. What's left behind could be a black hole spinning near the speed of light. It might even trigger a long gamma-ray burst, one of the most violent energy releases in the cosmos. Fast spin, huge mass. It's a recipe for cosmic chaos. Now for the second option, the stars narrowly avoid merging and die on their own. Each one could collapse into a black hole, but because they started off so close, those black holes would end up orbiting each other in a tight, shrinking spiral. Over billions of years, they'd drift closer until they finally smashed together in a spectacular merger. That collision would send out a blast of gravitational waves, the kind we first detected on Earth back in 2015 with LIGO. If this happens, the system we see today, the star merger, could be a glimpse into the past of a black hole merger yet to come. A ticking time bomb, quietly waiting to shake the universe. No matter what happens, the star merger is doomed to extremes, and it's teaching us a lot along the way. One thing is that it makes us question how we think about mass movement in pairs. Most theories say that stars this big should quickly trade mass, which would make them unstable and cause them to join. But the star merger has been able to stay in a very balanced state for millions of years, which shows how well the gravity and temperature forces work together. It also makes us think about how stars change over time in places with little metal. The Large Magellanic Cloud doesn't have as many heavy elements as the Milky Way. This changes the way stars lose mass. Because there is less metallic wind blowing stuff away, the stars hold on to more mass, spin faster, and act in different ways. This may help explain how extreme pairs like this can even form. And finally, it gives us a real-world laboratory for predicting gravitational wave sources before they happen. We're seeing, in real time, a system that may one day collapse, explode, or ripple the universe. OGLTR 56b, the boiling giant. We didn't know that planets could fry in their own skies until hot Jupiters became popular in exoplanet catalogues. But there was the boiling giant, a gas giant that is so close to its star that it's almost boiling away right now. As of 2003, this was one of the first exoplanets found using the transit method. It was also the first proof of something that seemed like science fiction. Big planets can orbit their stars closer than Mercury does to the Sun. The boiling giant orbits a sun-like star located about 5,000 light-years away in the constellation Sagittarius. It was spotted by the optical gravitational lensing experiment, which wasn't even looking for planets. It was searching for gravitational microlensing events, but stumbled across something even more bizarre, a star that dimmed slightly and regularly every 1.2 days. The repeated dimming showed that a planet was passing in front of the star. This method is now known as the transit technique. Later studies revealed the existence of a gas giant planet that was about 1.3 times the mass of Jupiter, but only 80% the size of Jupiter. This showed that it was squeezed together by the planet's strong gravity. But what's the real catch? The boiling giant is only 0.023 astronomical units from its star, which is about 2 million miles, or 23 times closer than Earth is to the Sun. By a large amount, that is closer than Mercury. From that far away, it only takes 29 hours for the planet to make one full circle. What a great example of a hot Jupiter it is. These are exoplanets that are big, gaseous, and heated up by their mother stars. But the boiling giant is one of the hottest Jupiters that has ever been found. Its dayside temperature is estimated at 2000 Kelvin or more, hot enough to melt iron, vaporize rock, and boil elements like sodium and potassium. The atmosphere is likely a chaotic mess of ionized gas, heavy metal vapor, and constant particle escape. It's not just hot, it's evaporating. Because of the intense radiation, the planet's outer atmosphere is literally expanding and leaking into space, forming a tail-like cloud of gas, not unlike a comet. It's being eroded, atom by atom, by the unrelenting blast of its star's heat. Think of Jupiter, but it's bright, swollen, and slowly turning into steam. Because the planet is so close to the star, it is held in place by tides that make one side always face the star. The day side is very hot because of this tide locking, but the night side could be hundreds of degrees cooler based on how well the winds move the heat around. On some very hot Jupiters, the winds can hit speeds of over 5,000 miles per hour as they try to keep the temperature even. The boiling giant, one of the first planets found by transit, also contributed to the development of methods for measuring extraterrestrial planetary atmospheres. Scientists have used secondary eclipse readings, when the planet goes behind the star, to pick out small changes in total light, even though it's hard because the planet is so far away. They can figure out the planet's heat output from these changes, even though they haven't actually seen it. Over time, planets like the boiling giant might lose so much mass that they shrink or even completely disintegrate. Some astronomers believe that hot Jupiters can be stripped down to their rocky cores, possibly explaining the origin of some super-Earths found close to other stars. In that sense, the boiling giant may be a preview of planetary death. It didn't just teach us about itself, it let a lot of other things come in. No one thought that gas giants could live in orbit so close together, but the boiling giant proved it. The gas giants in our solar system are far away and very cold. That idea was broken by this finding, which made us rethink how planets form and move. Could it be that these giants started out farther away and moved closer? Or maybe, in some situations, they can form right next to their stars, which was once thought to be impossible. XMMU J004243.6 plus 412519, the Andromeda anomaly. In early 2012, astronomers studying X-ray data from our galactic neighbor, the Andromeda galaxy, stumbled upon something so bright, so sudden and so puzzling that it simply didn't fit any known category of cosmic object. It was given the sterile catalog name XMMUJ004243.6 plus 412519, but what it represented was so extreme and unexplained that it became known as the Andromeda anomaly. This thing didn't just flash. It burst into X-rays over and over again, with a brightness that shouldn't have been possible for what it looked like, a neutron star or a black hole with the mass of a star. The first discovery was made by the XMM Newton X-ray Observatory of the European Space Agency. It was looking at Andromeda, which is about 2.5 million light-years away, as part of a normal scan. All of a sudden, this source lit up the X-ray detectors with light that was almost 10,000 ergs per second bright. In X-rays alone, that's more than 10 million times brighter than our Sun. This was disgusting for something in a different world. A dense object, like a black hole or neutron star, would have to be accreting, eating matter at a rate much faster than the Eddington limit for it to be this bright. That's the fastest a celestial body could theoretically eat matter before the radiation pressure causes approaching matter to be pushed away. There were rules that the Andromeda anomaly didn't follow. What then could it be? Astronomers first thought it might be a background quasar, which is a giant black hole that is very far away. But the spot was too near the center of Andromeda. The next thing they thought about was a supernova residue, but the light curve didn't match. Then, they checked to see if it could be a system of two stars with a black hole the size of a star gaining mass from a source star. That last theory seemed promising, except for the ridiculous brightness. If this object was a black hole just a few times the mass of our Sun, its luminosity was 100 times greater than theory allowed. This put it in a strange class of objects called ultra-luminous X-ray sources, or ULX. These are rare, extreme binary systems that shine far above what's considered physically possible for their size. The Andromeda anomaly was the brightest ULX ever detected in Andromeda. But even among ULXs, this one was an outlier. Its light curve was unstable, flaring, dropping, rising again, and fading over time. This wasn't a steady outburst like you'd see from a normal accreting black hole. It was chaotic, as if the object was choking on its own food. Follow-up views from NASA's Chandra X-ray Observatory helped rule out a number of possible locations. Since the object wasn't in the middle of the galaxy, it wasn't a giant black hole. It wasn't something in the Milky Way's center. It wasn't a very bright star. No matter what it was tight, small, and very hungry. So how do you explain an object shining far brighter than the Eddington limit, the point where radiation should push material away faster than gravity can pull it in? There are two possible answers, and both are pretty terrifying. First, it could be beamed emission. That means the object isn't radiating equally in all directions. It's blasting a narrow jet of energy directly at us, like a flashlight pointed in your eyes. This would make it seem way brighter than it actually is. If that's true, the object could be a microquasar, a stellar mass black hole firing off high-speed jets as it feeds, similar to the greedy eater in our own galaxy. It could be a neutron star that's not following the rules, not a black hole at all. This is the second and craziest option. It is now thought that some ultra-luminous X-ray sources, ULX, are neutron stars with magnetar-like magnetic fields that are so strong that they can pull in matter faster than science says they should. The material coming in is pushed toward the poles by these fields, which turn the energy into strong, narrow beams. Putting the light in one place keeps the system from blowing up. At least one other type of star is present in the Andromeda anomaly, if that is what we see there. It's one that goes against everything we think is possible. At this point, the object is no longer visible. It has faded back into the background, like a cosmic flare-up that was never meant to last. For a few months, though, it screamed across millions of light years, telling us that even nearby galaxies like Andromeda can be home to monsters that we can't explain. RxJ 1856.5-3754, the silent neutron. The sky is full of quasars, gamma-ray bursts, and magnetars that flash like dead stars having temper tantrums. But one neutron star has chosen a different path. It is silent, not a beat. Don't use lights. There were no explosions. It was just a steady, soft glow. We call this strange star RxJ 1856.5-3754, and it is one of the nearest neutron stars we know of to Earth. But even though it's close and clear, it's still very quiet. It's called the silent neutron because of this. It was found by Rosat, the German X-ray telescope, in the 1990s. The silent neutron is in the constellation Corona Australis, 400 light-years away. In cosmic words, that's pretty close to next door. It gives off clear, bright, and stable X-rays. However, it refuses to pulse, which makes it a very strange thing. Neutron stars form when massive stars collapse at the end of their lives. These remnants are only about 20 kilometers wide, yet they pack in more mass than the Sun. Most neutron stars emit beams of radiation from their poles. And if one of those beams sweeps past Earth, we see it flash on a regular rhythm, like a cosmic lighthouse. These are pulsars, and they're how most neutron stars are detected. But the silent neutron, no beam, no pulse, just a smooth thermal X-ray glow. It's like looking at a glowing coal, except this coal is a sphere of degenerate nuclear matter crushed by gravity into a near-perfect sphere and glowing softly at a temperature of around 700,000 Kelvin. That glow from the silent neutron is pure blackbody radiation, something almost unheard of in space. Most cosmic objects have complex light signatures, filled with lines from atoms, molecules, or magnetic fields. But this one, it emits smooth, featureless radiation, just like the perfect examples shown in physics textbooks. It's clean, it's simple, and it's unsettling. At first, this simplicity baffled scientists. Was this even a neutron star? It didn't show the usual pulsations, which made it look more like a white dwarf. But the temperature was too high, and the size too small for that. Only when astronomers used Hubble's parallax data to measure its distance and radius did things become clear. It had to be a neutron star. Nothing else could be that small and that hot. So why doesn't it pulse like most neutron stars? There are a few possible answers. One idea is pole misalignment. The star might have a beam like a normal pulsar, but we just don't see it, maybe because the beam is too narrow or because it never sweeps across Earth. That would make the silent neutron a quiet pulsar, invisible to us except for its thermal glow. Another possibility is true polar cap emission. In this model, the X-rays come from a small hotspot on the star's surface, a polar cap. If that spot always faces us because of how the star spins, the light would look steady, not pulsing. And finally, it might just be a different kind of neutron star altogether. The silent neutron could be part of a rare group known as the Magnificent Seven, a handful of nearby young neutron stars that glow with thermal X-rays but don't emit strong radio signals. They're quiet, isolated, and still cooling from their violent births. The silent neutron is the brightest and closest of them all, a mysterious, silent beacon from a class of stars that break the usual rules. This thing moves. It's going about 100 kilometers per second through space, and it's leaving a bow shock, which is a ripple in the gas between the stars. It shines and moves through the sky like a cosmic bullet, leaving a soft trail of chaos behind it. The silent neutron has had a huge effect on theoretical physics, even though it is very quiet. Scientists can put strict limits on the neutron star equation of state by looking at its clean temperature spectrum. This lets them study how matter acts under pressures and densities that we can't make in the lab. Researchers can test different models of ultra-dense matter, such as those involving quark matter or unusual particles, by looking at how its light bends near the surface and how big it looks at different wavelengths. This humble object has also helped disprove some wild ideas. At one point, its clean spectrum was so baffling that some scientists even proposed it might be a bare quark star, a hypothetical object made of pure up, down, and strange quarks. That theory has mostly fallen out of favor, but the silent neutron still keeps us guessing. A neutron star that doesn't flare, doesn't pulse, doesn't explode, and yet might be one of the most scientifically valuable in the sky. It doesn't shout like a magnetar or scream like a pulsar. It just glows, quietly, with the memory of a supernova long past. GW 190814, The Mass Gap Mystery. On August 14, 2019, something rippled through space. That ripple, a distortion in the very fabric of space-time, passed through Earth, setting off alarms at the LIGO and Virgo gravitational wave detectors. But this wasn't just any wave. It was GW 190814. And when scientists looked at the data, they found something that shouldn't exist. This event marked the merger of two incredibly dense objects. One was a black hole about 23 times the mass of the Sun. But the other, that's where things got strange. It had a mass of 2.6 times the Sun, placing it right in the middle of what scientists call the mass gap. Here's what that means. In stellar evolution, dying stars usually end up as one of two things. If a star isn't very massive, it collapses into a neutron star, a compact object made almost entirely of neutrons, with a maximum mass around 2.2 times that of the Sun. If the star is more massive, It collapses further and becomes a black hole, an object so dense that not even light can escape, starting at around 5 solar masses. But in between those two, that's the mass gap, a range where, until recently, we hadn't seen anything survive. So finding an object with 2.6 solar masses, it's like discovering something that shouldn't exist, challenging everything we thought we knew about how stars die. So what about objects between 2.2 and 5 solar masses? That's the mass gap, a zone where, until the mass gap mystery, we had never observed any compact object. Neutron stars weren't expected to get that heavy, and black holes weren't expected to get that light. The models said it shouldn't exist. But now, out of nowhere, we had detected something merging with a black hole that weighed just 2.6 times the mass of the Sun. Too massive to be a neutron star, too light to be a black hole. So, what was it? This mystery sparked one of the biggest astrophysics debates in years. One possibility is that it was the heaviest neutron star ever discovered. If that's true, then somehow this object resisted collapsing under its own gravity, holding itself together against all odds. That would push our understanding of neutron star physics to the edge, suggesting that these stars can be even denser and more massive than current models allow. It could even mean that exotic matter, like a core made of pure quarks, really exists inside. The second possibility? It was the lightest black hole ever found. That would mean black holes can form from smaller stars than we thought, or through completely different processes we haven't figured out yet. Maybe it was born from the collapse of an unusually massive white dwarf, or from the merger of 2 neutron stars that formed a tiny black hole instead of a larger one. And then there's the third, wildest option. It's something entirely new. Some fringe theories say it could be a boson star, a hypothetical object made of unknown particles, or even a chunk of exotic matter, like dark quark nuggets. There's no hard evidence for those yet, but the fact that this object, part of event the mass gap mystery, landed right in the forbidden mass gap. That alone cracks open the door to new physics. The mystery doesn't end with mass, though. What's even stranger is that we didn't see any light. When 2 neutron stars join, they usually make a kilonova, which is a burst of electromagnetic energy, optical, X-ray, and gamma, as they hit each other and throw matter into space. We didn't see anything with the mass gap mystery, though. Not a light. No trash. Only waves of gravity. This means the black hole probably took the smaller item whole, without breaking it up. It's like a pebble going into a pond. For that reason, it seems likely that the smaller object was very dense, possibly a black hole, or at least a neutron star without any extra material to remove. A very unusual feature of the system was that the mass ratio was about 9:1, which is not often seen in known binary mergers. Because of this unbalance, the smaller item may have spiraled in faster and left less of a mark, like when you drop a marble into a vacuum cleaner. The event gave scientists incredible precision data: the spin of the black hole, the mass of the companion, the speed of the inspiral. It all checked out, except for the part where one of the objects shouldn't exist. The mass gap mystery is helping us refine Hubble's constant, the rate at which the universe is expanding. By comparing gravitational waves with any possible light emission, even though we didn't see any here, researchers can triangulate cosmic distances and get better measurements of the universe's size and age. GRB 060614, the missing supernova. On June 14, 2006, a gamma ray burst lit up the sky. Nothing unusual at first. It was long, lasting about 102 seconds, which instantly flagged it as a long-duration GRB, the kind typically associated with the explosion of a massive star in a supernova. Astronomers did what they always do. They aimed every telescope they could at the event's location, expecting a brilliant supernova to follow in the days ahead. It never did come, though. There's no light trace, no star going down. There is no light sound, nothing. The event was called GRB 060614, and it shocked people who study astronomy. This sound was supposed to be a death cry, but it came off more like an act of disappearance. This is how GRB 060614 got its scary name, the missing supernova. It is thought that very large stars, especially ones that spin quickly and turn into black holes at their centers, cause long GRBs more than 2 seconds when they collapse. This is called the collapsar model. The events are loud, messy, and intense, and most importantly, they almost always cause a supernova that can be seen. A supernova is a bright flash of light and a slow fading light curve that happen when a star explodes and sends heavy particles into space. Short GRBs, less than 2 seconds, usually come from things like neutron star mergers, which don't produce traditional supernovae. They might give off a kilonova, which is much dimmer, redder, and shorter-lived. Now, GRB 060614 lasted over 100 seconds. That's textbook-long GRB behavior. But the host galaxy, wrong type. It was an old, low star formation dwarf galaxy, the kind where massive stars aren't being born often. That already raised questions. Still, maybe it was just a rare occurrence. Despite a wave of follow-up observations, including deep scans from the Hubble Space Telescope, no supernova ever appeared after GRB 060614, not even a faint one. This wasn't just a weak explosion. It was completely missing. And the data was so precise, it ruled out any supernova, even 100 times dimmer than the kind we normally see with long gamma-ray bursts. So what caused it? One idea is that this was a new kind of merger. Some astrophysicists suggested it might have been a neutron star merging with a black hole, a type of event we'd only theorized about back then. If the black hole swallowed the neutron star without ejecting much material, it could create a long gamma-ray burst from the feeding disk, but without the glowing cloud of a kilonova. That would explain both the long burst and the eerie lack of visible light. Another possibility? A failed supernova. In this case, the massive star would have collapsed straight into a black hole with no outward explosion. Instead of blowing apart, the core just fell in on itself. The gamma rays came from jets powered by that collapse, but the rest of the star got swallowed, leaving nothing behind for telescopes to see. No bang, just silence. And finally, there's a third, more radical idea. A new class of gamma-ray burst. This event might not fit into either of the two classic categories, collapses or mergers. Maybe it was a hybrid, or something completely new. An underpowered collapsar? A long-lasting merger? Whatever it was, GRB 060614 may have given us the first clue that the universe has more ways for stars to die than we ever imagined. Adding to the mystery, follow-up studies of similar long GRBs without supernovae began popping up. GRB 111005A showed the same behavior. So did others. This wasn't a fluke. It was a pattern. Something was going on in the universe that we weren't prepared to see. GRB 060614 didn't just shake up theories. It challenged the way we classify gamma-ray bursts altogether. Before this event, the rule was simple. Short bursts came from mergers. Long ones came from collapsing stars. Clean and easy. But then came 060614, a long-duration burst with none of the usual signs of a collapsing star. No supernova, no glowing debris, just a ghost of light and a lot of questions. After that, astronomers realized duration alone isn't enough. Now, they look at a whole list of clues: the type of galaxy the burst came from, the shape of its light curve, how the afterglow fades, the hardness or energy of its spectrum, and whether a supernova follows. Even now, 17 years later, GRB 060614 refuses to be boxed in. It doesn't fit. It doesn't follow the rules. It just happened. And now it sits in the cosmic record like a riddle with no answer. PSRJ 1748-2446 AD, the Speed Demon. Neutron stars spin like tops in nature, but PSRJ 1748-2446 AD is the one that's turning the table over. Not only is this thing fast, it's also the fastest spinning neutron star ever found, going around 716 times per second. Indeed, it takes 1.39 milliseconds to make one full turn. From what we've seen, nothing in the universe spins faster and stays alive. The star in question is not a light one. The Speed Demon is a collapsed star core, which is the leftover matter from a supernova explosion. It is now a 20-kilometer wide ball with more mass than the Sun. It is made up of degenerate nuclear matter, which means that protons and electrons have been squished together to form neutrons. It is so dense that a teaspoon would weigh as much as a rock. The speed is faster than a home blender. Discovered in 2004 using the Green Bank telescope in West Virginia, the speed demon was found in a region called Terzan 5, a dense globular cluster located about 18,000 light-years away in the constellation Sagittarius. This cluster is packed with stars, so tightly in fact, that stellar collisions and near misses are common. It's the perfect environment for exotic binary systems. This speed monster got its spin in the same way. Neutron stars don't really spin this fast by themselves. A young neutron star that has been through a supernova may spin several times every second. They slow down over time though, unless they get a push. The boost comes from a binary partner. The speed demon used to be a part of a low-mass X-ray binary system, which means it had a small normal star going around it. Over millions of years, the neutron star sucked matter off of its partner. The gas that came in had rotational momentum, which made the neutron star spin up like a potter's wheel picking up speed. This process is called recycling, and it turns sluggish neutron stars into millisecond pulses, neutron stars that rotate hundreds of times per second, like precision clocks powered by gravity and theft. But the speed demon didn't stop at hundreds. It went all the way to 716 Hz, or 716 rotations per second, the physical upper limit of what neutron stars are predicted to endure. Why? Because there's a risky area. The centrifugal force at the equator of a neutron star can be stronger than gravity if it spins too fast. This can cause the star to actually fly apart, losing mass or splitting open. This limit is thought to be between 1000 and 1200 Hz, but it depends on what the neutron star is made of inside, and the speed demon is very close to that edge. We can learn a lot from its spinning speed about the equation of state, which is a mathematical model of how matter acts at nuclear levels. We can't make that happen on Earth, so stars like this one are used to study natural physics. Its ability to stay together helps us rule out some ideas and learn more about neutron degeneracy pressure, nuclear interactions, and maybe even quark matter. What's also strange? Despite its extreme speed, the speed demon is not particularly bright in X-rays. That's because its accretion period is over. Its companion has been stripped to the bone. And unlike many pulsars, it doesn't emit strong beams of radio waves pointed at Earth. It was discovered only because of a lucky alignment and sharp timing, during a brief window when it was detectable. It is thought to have a mass of about 1.35 solar masses, which isn't very heavy for a neutron star, but could be what keeps it alive. With less mass, there is less gravity to fight, so it might be able to spin faster without snapping apart. A few scientists think this object may be just on the edge of falling apart, keeping itself together by the thinnest of physical lines. There may be neutron stars that spin 800, 900, or even 1000 times per second, but we haven't been able to find them. If their beams aren't pointing at Earth, or if their pulses are too weak, they might just be ghosts that are speeding through the sky without anyone knowing. The speed demon is the universe's fastest known object that isn't very small, a dead star that has been shrunk down to the size of a city and is moving so fast that it defies the laws of physics. It does this without falling apart, bursting, or making any noise. MS 0735.6 plus 7421, the cluster bomb. People know most black holes for what they eat. Some, though, are known for what they blow up. One of the most powerful and large-scale explosions ever seen in the universe is deep inside a galaxy cluster, more than 2.6 billion light-years away. What is it? MS 0735.6 plus Civ to N. This isn't a normal group of galaxies. A giant black hole is at the center of a very large circular galaxy. But this black hole did something truly amazing. It erupted with such force that it made two huge holes hundreds of thousands of light-years wide in the hot gas surrounding it. It's clear that this wasn't a supernova. There wasn't a gamma-ray burst here. It was a black hole making bubbles in space, and the amount of energy it released was the same as hundreds of millions of supernovae going off at the same time. Using NASA's Chandra X-ray Observatory, astronomers imaged the cluster bomb and noticed something odd. The hot gas, also known as the intracluster medium, had two enormous dark voids. These regions were empty of X-ray emitting gas. They weren't caused by chance. Something had blasted this material outward. And the only suspect that could unleash that kind of force? A feeding supermassive black hole. This black hole didn't just eat matter, though. It also put huge amounts of energy back into the universe. This is called active galactic nucleus AGN feedback. In this case, the black hole sent out relativistic jets, which are thin beams of particles moving very close to the speed of light. These jets punctured holes in the gas around them, heating it and moving it around as they expanded. And the scale? Absolutely mind-blowing. Each of the cavities carved out by this black hole explosion is about 600,000 light-years wide. That's 6 times wider than the entire Milky Way galaxy. To create those holes, scientists estimate it took around 10 to the 62nd power ergs of energy. That's a 1 followed by 61 zeros, an almost unimaginable amount. This isn't just the most powerful black hole eruption ever recorded. It's one of the most energetic events in the universe since the Big Bang itself. This cluster bomb effect is more than just impressive. It's deeply important to understand how galaxy clusters evolve. In the absence of such outbursts, the hot gas in galaxy clusters should cool over time and collapse into new stars, what we call a cooling flow. But in clusters like MS0, 73, 5.6 plus 7421, this doesn't happen. Why? Because AGN outbursts like this reheat the gas, preventing it from collapsing, effectively quenching star formation on massive scales. The black hole's blasts every few 100 million years seem to keep the galaxy cluster in check by stopping its growth. A space control, a temperature controller, a timed bomb. Today is a quiet day for this black hole. Whatever happened in the past isn't happening now, which means we're seeing the results of a single event that happened a long time ago. A volcano erupted a long time ago and is now stuck in the sky. The blast radius is still growing after hundreds of millions of years. We're still not sure what caused such a huge explosion. It's possible that the black hole got a quick flood of matter, which could have come from a star that broke apart or intergalactic gas. Not all of that stuff disappeared into the event horizon. As some of it was turned into kinetic energy, it was hurled into space in a storm that still changes the galaxy cluster today. GRB 080916c, the Gamma God. When it comes to raw power, few things in the universe can rival a gamma-ray burst. But even among those cosmic titans, one burst stands alone. The one that rewrote the upper limit of cosmic violence, GRB 080916c. Observed on September 16, 2008, it didn't just break records, it obliterated them. This wasn't just a space blip. It happened over billions of light-years away in the constellation Carina, sending energy our way from about 12.2 billion light-years away. And even though it was so far away, it was so strong that NASA's Fermi Gamma Ray Space Telescope could clearly see it. The Gamma God unleashed an estimated 8.8 times 10 to the 5th power ergs of energy. And that's just in gamma rays. To put it in perspective, that's the equivalent of about 9,000 type Ia supernovae exploding all at once. In a single burst lasting only seconds, it released more energy than our Sun will emit over its entire 10 billion year lifetime. It's one of the most powerful explosions the universe has ever shown us. A cosmic flash so intense, it redefined what we thought was even possible. And it didn't just shine, it blazed in extremely high energy gamma rays. Fermi's Large Area Telescope, LAT, detected photons up to 13.2 billion electron volts, GeV, the most energetic gamma rays ever observed from a GRB at the time. That's billions of times more energetic than visible light. Even more mind-blowing, these high-energy photons arrived simultaneously with lower-energy ones. This allowed scientists to test one of the strangest ideas in modern physics, quantum gravity, which predicts that light of different energies might travel at slightly different speeds through the quantum foam of spacetime. But in GRB 080916c, there was no delay. The photons, despite differing by orders of magnitude in energy, arrived together. That ruled out several speculative models of space-time distortion. putting new limits on theories of Lorentz invariance violation. In other words, even the most exotic versions of space-time had to bow to this burst. So what made it happen? The most popular idea about the Gamma God is that it was caused by a star that was over 50 times as big as our Sun collapsing into a black hole, which set off a long-lasting GRB. When this kind of star falls apart, matter and energy shoot out along its rotating poles at almost the speed of light. A gamma-ray burst happens when one of these jets is aimed straight at Earth. This burst was different, though, because of how big and fast it was. Scientists think the jets from the Gamma God were moving at Lorentz factors above 1000. This means they were so close to the speed of light that time would have seemed to slow down a lot inside the jet. The ejector is now one of the fastest moving things that has ever been found coming from an astronomical source. The duration of the burst, over 60 seconds, and the way its light curve evolved showed complex internal shocks within the jet, indicating a multi-phase explosion, possibly involving magnetic reconnection, turbulence, and fragmentation of the collapsing star's core. And despite all this chaos, the jet remained incredibly focused. That narrow beam is the only reason we even saw it, and the only reason Earth wasn't vaporized by it. Had this event occurred in our own galaxy, and had the beam hit us directly, it could have stripped Earth's atmosphere and caused a mass extinction event. Thankfully, it was 12.2 billion light-years away. That also means the burst happened before the universe was 2 billion years old. At that time, huge stars had already formed, lived, and died in these dramatic ways. A gamma-ray burst engine and the black holes that power it have been working since the beginning of time. Astronomers see the Gamma God as more than just a new record. It serves as a guide. It is used to compare every new GRB found to the burst that was brighter than galaxies, made quantum theory look silly, and moved through the universe without changing for more than 12 billion years. M82X-2, the impossible neutron. Astronomers found something that didn't follow the rules in the starburst galaxy Messier 82, which is about 12 million light-years away. There was no black hole there. There was no star. It was a neutron star, but not just any neutron star. It should have torn itself apart because this one was giving off so much energy. Based on what we thought we knew, it shouldn't be there. That's why it's named the impossible neutron. When the NOSTAR X-ray telescope detected it in 2014, researchers assumed it was another ultraluminous X-ray source, ULX, a compact object, usually a black hole, feeding so fast it shines like a lighthouse in X-rays. ULX is bright, but the impossible neutron was too bright, radiating about 10 to the 40 ergs per second, or roughly 100 times the Eddington limit for a neutron star. The Eddington limit is the point where radiation pressure balances gravitational pull. If an object emits more than that limit, the energy should blow away incoming matter, making further accretion impossible. For a neutron star, a crushed core of matter just 20 kilometers wide, the Eddington limit is pretty strict. And yet, here was M82X-2, breaking it by orders of magnitude. How does it do that then? First, it wasn't a black hole at all, which was a surprise. After making more notes, something amazing was found. Pulse from M82X-2. Like a clock, it sends out a spike of X-ray energy every 1.37 seconds. That's the sign of a pulsar. So this thing is definitely a neutron star. It's not a black hole, but the dense remains of a supernova that's spinning like a lighthouse. It was an ultra-luminous X-ray pulsar, ULXP, which is one of the strangest and most extreme types of things known to exist in the universe. Let's look at how this could be possible. The most popular idea right now is that the impossible neutron is magnetically filtered. Neutron stars have very strong magnetic fields that push things that fall toward them onto their magnetic poles. This makes thin streams of accretion where matter hits the surface and makes X-rays. The energy doesn't have to go out in all directions. These columns can focus it into beams. This beam effect means the object might appear more luminous than it truly is, like pointing a flashlight at your eyes versus looking at a bare bulb. If the beam is aimed toward us, The observed luminosity can far exceed the Eddington limit without actually violating it locally. But even with beaming, the energy levels are staggering. The neutron star is likely consuming mass at an astonishing rate, swallowing the equivalent of Earth every few weeks, and doing so without collapsing into a black hole. It's a balancing act that challenges our understanding of how gravity and radiation interact at the edges of physics. The impossible neutron shows stable pulsing over time, suggesting that its feeding is not chaotic. The pulsar is somehow maintaining order within chaos, a well-behaved demon defying the laws of accretion physics. This discovery turned the study of ULX on its head. For decades, most scientists believed these objects could only be black holes, since only black holes could pull in material fast enough to shine that brightly. But now we know that neutron stars can masquerade as black holes, as long as they're magnetized and well fed enough to get away with it. Scientists have had to rethink how many neutron stars could be living in plain sight by pretending to be black holes because of M82X2. If this one object can fool us, then there could be hundreds of ULX sources in faraway galaxies that we have been calling the wrong thing. It also makes us question how we think stars die and how compact objects form. What else can neutron stars do if they can be this big, this hungry, and this stable? Could some of them change into black holes with a middle mass? Could they cause different kinds of supernovae? Could they have something to do with short radio waves? Lens-Thirring binary detection, 2015. The space-time twister. Suppose a planet going around the Sun, but its orbit doesn't follow a smooth circular path. Instead, it wobbles. This isn't because another planet is pulling on it. It's because space-time is being pulled and bent, like taffy. That's not made-up science fiction. It's called frame dragging, and it was finally seen in a system of two stars in 2015. It was one of the strangest proofs of Einstein's theory of general relativity. What happened? How lens-Thirring binary detection works. What's the name? The twister in space and time. Back in 1918, Austrian physicists Josef Lense and Hans Thirring proposed a strange consequence of Einstein's new theory. If a massive spinning object rotates, it should drag the space-time around it, twisting the very fabric of the universe. Think of it like swirling honey with a spoon. Anything nearby gets pulled into that motion. In astrophysics, this is called frame dragging. But it's ridiculously hard to find. NASA's Gravity Probe B confirmed frame dragging close to Earth in 2004, but the effect was very small. Scientists really wanted a way to see it in a much harsher setting, where space-time is thicker, tighter, and under a lot of pressure from gravity. Here comes PSR-J 1906 plus 0746, and then, more firmly, a system called PSR-J 0737-3039AB, which is the first known double pulsar system. It looks like two neutron stars are locked in a death spiral dance, only the distance of one Earth-moon from each other. In 2015, after years of precise timing observations, scientists confirmed that one of the pulsars was experiencing precession, a slow wobble in its spin axis. But not because of another star tugging on it. It was precessing because the other pulsar was twisting the space-time around it. That's frame dragging, observed in a binary system for the first time, in the wild. Neutron stars are already extreme. They cram more mass than the Sun into a sphere just 20 kilometers wide. When such a star spins, its angular momentum drags nearby spacetime along for the ride. The companion pulsar in the binary moves through this twisted space, and its orbit responds in subtle but measurable ways. Scientists saw relativistic rotation in the pulsar's radio beam in particular. Its signal, which looked like a lighthouse, moved in a way that Newtonian gravity couldn't explain. They could only predict and match the wobble seen in the data by taking frame dragging into account in the calculations. It was a eureka moment. This wasn't just Einstein being right again. This was Einstein being right in one of the most extreme environments in the universe. A neutron star orbiting another neutron star in a relativistic death spiral. What this means is very important. First, it shows that frame dragging is real and not just a theory or something that only happens on Earth. It's real in the universe. It changes how stars, pairs, and maybe even black holes move. Second, it lets scientists try different theories of gravity, since many of them can't predict or explain this. This find shows what LIGO and other gravitational wave trackers might be able to find in the future. We now know how to find the signature that shows up when neutron stars and black holes join. Their frame dragging should twist and spin spacetime in crazy random ways. This binary system also helps refine our measurements of other fundamental constants, like the moment of inertia of neutron stars, which in turn can help constrain nuclear physics and the equation of state for matter at ultra-high densities. It's not just a gravitational experiment, it's a peek into the core of collapsed stars. Cahis 8462852, the WTF star. People who study the stars expect strange things to happen. It happens every once in a while, though, that something so strange and hard to explain that even experts give up and say, "What the?" That's exactly what happened when scientists found the star KIC 8462852, which is also known as Tabby's star, or less formally, the WTF star. Let's rewind to 2009, when NASA's Kepler Space Telescope began scanning the skies, looking for exoplanets by detecting dips in a star's brightness. Most dips were regular, repeating patterns caused by planets transiting their stars. But one star, the WTF star, located about 1,470 light-years away in the constellation Cygnus, didn't play by the rules. Instead of smooth, predictable dips, Tabby's star flickered like a dying light bulb. In 2015, a team led by Tabitha Boyajian analyzed the data and found that the star's brightness had plunged by up to 22% at random intervals. An absurdly deep dip, way too large for a planet. Even Jupiter only blocks about 1% of our sun's light when it transits. There was also no trend, no space, not a beat. The dips didn't happen at regular times and were very uneven. One dip could last 5 days, while another could last 80. It looked like big, sharp things were randomly moving in front of the star. It looked like there was some kind of disordered, hazy swarm around the star. As you might expect, this led to the most popular and debated science idea in recent years. What if it's aliens? No joke, one of the ideas put forward was a megastructure, which looks like a Dyson swarm and is made up of energy-gathering satellites orbiting around the star of a powerful alien society. Not that experts thought this was likely, but it was so strange that at first it couldn't be ruled out. SETI even aimed radio telescopes at Tabby's star, hoping to catch a signal from intelligent life. But they found nothing. No beacons, no transmissions, just a star behaving in ways that defy all logic. With no obvious answer, new theories began to emerge. One idea was comet swarms. Maybe a massive cloud of comets or icy debris was passing in front of the star. But to block 22% of the star's light, you'd need a huge, tightly packed swarm behaving in a way we've never seen before. Another possibility was dust clouds. Maybe the light dips were caused by strange types of dust with unusual particle sizes, but infrared scans didn't show the kind of heat that all that dust should be giving off. There was also the theory of a warped planetary debris disk. Maybe the star had devoured a planet, and the leftovers were scattered unevenly in orbit. It sounds dramatic, but it still doesn't quite match the scale or pattern of the dimming. Some proposed intrinsic stellar variability. Maybe the star itself is unstable or has unusual magnetic cycles. But here's the catch. Tabby's star is an F-type star, and others like it don't show this kind of bizarre, unpredictable behavior. Photographs from the past show that Tabby's star has been slowly dimming over the past 100 years, in addition to the short-term dips that were studied later. In more recent Kepler and ground-based readings, the star's light has continued to drop by about 3% over 4 years. It's not just getting darker all at once, it's getting darker over time. The long-term dimming can't be easily explained by something going around the star. It points to a long-lasting, big process, possibly a huge disk or a cloud of stuff that is slowly being added to. But once more, there is no infrared heat trace. If something is blocking light, it's either very cold or made of a strange material. In 2018, new observations suggested that the dips were more pronounced in blue light than red, which means they were likely caused by dust, not solid objects. But that just leads to another question. What kind of dust behaves this way, in this configuration, around only this star? Still no answer. OGL 2011 BLG 0462, the Hidden Reaper. There are some very dangerous things in space that you can't see. They don't shine, they don't blow up, they don't even whisper, they drift. It's cold, dark, and dangerous. Astronomers weren't even sure they existed for a long time. Then came the Hidden Reaper, the first isolated stellar mass black hole ever discovered, completely invisible, and detected only because it bent light. Nicknamed the Hidden Reaper, this object wasn't found in the usual way, by its X-ray emissions or its effect on a companion star. No, this Reaper was caught red-handed, distorting the light of a distant star using nothing but its gravitational pull. That's gravitational microlensing in action, and it's one of the most mind-blowing tools in modern astronomy. Consider looking at a star in the distance. Usually, its light gets to us without any problems. But if a big object, even one that doesn't give off any light, moves in front of it, its weight can bend and focus the light from the background star like a magnifying glass. In a very clear pattern, that faraway star gets brighter for a short time and then gets darker. Back in 2011, the Optical Gravitational Lensing Experiment, OGL, saw something strange in this way. A star got much brighter, but no visible object seemed to be to blame. Years later, more data from NASA's Hubble Space Telescope showed something shocking. The object that was lensing had mass, but no light that could be seen. It wasn't a star. The star wasn't a brown dwarf. It wasn't a world. It was a black hole that lived in the middle of nowhere and floats like nothing. That's very important. It is thought that most black holes live in pairs with stars that they slowly eat. We can see them because as they eat stuff, they send out X-ray flares. But what about black holes that are just floating through the galaxy? These are the remains of stars that blew up a long time ago and were thrown out of their homes. Theorists have long predicted there should be hundreds of millions of these silent killers. But without a companion or accretion disk, they're invisible until they happen to line up perfectly with a background star. And that's exactly what happened with OGL 2011 BLG 0462. Using both OGL and Hubble data, scientists measured the precise distortion and motion of the background star over 6 years. The results were jaw-dropping. The lensing object had a mass of about 7 solar masses, the sweet spot for a stellar mass black hole, and it was moving through space at around 45 kilometers per second. No light, no X-rays, just a ripple in space-time, a gravitational fingerprint. For the first time ever, humanity directly detected a lone black hole, not orbiting a star, not feeding, not glowing, just drifting through space, invisible but real and trackable. This discovery opens a whole new frontier in black hole research, one that doesn't rely on light, but purely on gravity. The implications are massive. It proves that supernova explosions can launch black holes out of their home systems, turning them into silent, wandering predators. It confirms what stellar models have long predicted, that the galaxy should be filled with these rogue black holes. It also gives scientists a brand new way to find them, without needing X-rays or visible light. But perhaps most importantly, it reveals something even deeper: how much of our galaxy is still hidden in the dark, waiting to be found. If one black hole can be found this way, it means millions more are out there, drifting through space, undetected, some closer than we'd like to imagine. These hidden reapers could be passing near star systems, disturbing comets, altering orbits, or just quietly waiting in the dark. The hidden reaper wasn't just found by chance. It was a surprise attack in space, and we were lucky enough to see the mark in the lens of a star in the background. It doesn't have a face, a glow, or a sound. It is what it is. PSR J0 348 plus 0 432, Einstein's labrat. Some stars stop shining and become quiet. Some people go out with a bang, but a very small number keep going like cosmic clocks long after they die. Meet PSRJ 348 plus 0 432, a dead star that Einstein used to test his ideas a lot. This extreme pulsar, which scientists called Einstein's labrat, gave them a once-in-a-generation chance to test general relativity to its limits, and it did not fail. So what exactly is this thing? Einstein's labrat is a pulsar, a type of neutron star that spins rapidly and sends out beams of radio waves like a lighthouse. But this one is special. It's part of a binary system, orbiting tightly with a white dwarf companion. That alone isn't too rare. What makes this pulsar unique is its mass. At 2.01 times the mass of the Sun, packed into a sphere only about 20 kilometers across, Einstein's labrat is one of the most massive neutron stars ever measured. It's pushing the very theoretical limit for how massive a neutron star can get before collapsing into a black hole. That makes it the ideal place to test Einstein's ideas. General relativity says that in a binary system like this, certain things will happen. Time will slow down, gravitational redshift will happen, and orbits will break apart due to gravitational waves. A lot of hard math goes into it. But because this pulsar sends out radio waves at exact times, we can measure how it's acting down to the microsecond. Take a look at that, a star that is billions of years old and dead, ticking away so exactly that we can see tiny changes in its path just because of the pull of space-time. In fact, experts did just that. Astronomers watched the pulsar's pulses with radio antennas all over the world and matched them to what general relativity said would happen. The end result, right on. Einstein made a lot of strange predictions, like that orbits would break apart and time would speed up. All of these predictions came true in this crazy high-gravity system. It's like watching planets fall around the Sun, but at 1,000 times the speed and 1,000,000 times the gravity. Instead of centuries, these orbits evolve in decades. And instead of vague clues, we get precise, testable data. The companion star, the white dwarf, is tiny and dim, but scientists were able to measure its spectrum using the Very Large Telescope, VLT, in Chile. That gave us its mass and orbital speed, allowing even more accurate tests of gravitational theory. And this all matters, because alternative theories of gravity, ones that try to go beyond Einstein, often break down in extreme conditions. If the universe has some deeper rulebook hiding under general relativity, it's going to show up in places like this. But there were no holes found, no strange changes. Einstein can take one more winning lap from beyond the grave. Let's talk about how important it is that this pulsar has a lot of mass. For a long time, physicists have been interested in how heavy a neutron star can get before it turns into a black hole. It's not clear where the Tolman-Oppenheimer-Volkoff limit is, but we think it's between 2.2 and 2.3 solar masses, based on what kind of strange matter is inside the star. Einstein's labrat is dangerously close to that edge. Its existence alone tells us that neutron stars can survive just past 2 solar masses, which rules out a whole bunch of theoretical models. If this neutron star has something weird inside, like quark matter or a superfluid core, it might be what's holding it up against collapse. So this isn't just a test of gravity. We're also learning about the most basic science of matter when it's under pressures billions of times greater than anything we can make on Earth. And this system is still not finished. For the pulsar to lose energy as it sends out gravity waves, its orbit will get smaller. It might get so close to the white dwarf one day that they join, which could either cause a huge supernova or a slow collapse into a black hole based on how much mass is left. GRB 111209A, the marathon burst. GRBs are mostly short and dirty explosions that go off, scream across the universe for a few seconds, and then go away. They're like flashbangs in the universe. But in 2011, scientists saw a GRB that wouldn't go away. It had a high-energy temper tantrum that lasted over 7 hours, which is how it got the name the marathon burst. The event was catalogued as the marathon burst, and from the start, it didn't behave like any normal gamma-ray burst. It was first detected on December 9, 2011 by the SWIFT satellite, which automatically points telescopes toward high-energy cosmic events. But this time, something was different. It just kept going. SWIFT's gamma-ray instruments watched it flare for over 25,000 seconds. That's 7 hours straight, compared to the usual 20 to 100 seconds for long GRBs. To understand how extreme this is, imagine a black hole being born, a violent collapse of a massive star. The core implodes, jets of gamma rays blast outward, and usually that process burns out fast. The fuel runs out, the star's death rattle ends. But in this case, it was like the engine never stopped. The gamma ray burst from Einstein's labrat lasted so long and released so much energy that it shattered existing models. Scientists were left asking, what kind of monster star could possibly fuel this kind of explosion? Here's what we do know. The marathon burst came from a galaxy about 3.5 billion light-years away. After the initial blast, it produced an optical afterglow so bright and long-lasting that astronomers were able to study it for weeks. A rare gift when it comes to gamma-ray bursts. And here's the strange part. Despite how powerful the explosion was, there was no clear supernova visible right after the burst. That missing piece raised even more questions and suggested this was no ordinary stellar death. Now let's talk about where this monster came from. There are two main ideas, and both involve extreme cosmic powerhouses. It's potential that a blue supergiant will die. Wolf-Rayet stars, which are big but packed and have already lost their outer layers, are usually the source of long gamma-ray bursts. Blue supergiants, on the other hand, are very big, sometimes over 100 times the Sun's mass, and have thick layers of hydrogen gas around them. The idea is that if one of these stars falls apart into a black hole, while still feeding its disk with material from the outer layers, the jet that forms could keep going for hours. That steady flow of fuel could explain the very long burst. The problem is that blue supergiants shouldn't be able to make GRBs. Their thick hydrogen shells often suffocate the jets before they can even start to move. That means that if this star did it, it either beat the odds or showed that our understanding of how stars die is very incomplete. The other theory is a magnetar going completely berserk. A magnetar is a neutron star with an insanely strong magnetic field, the leftover core of a star that didn't collapse into a black hole. If the marathon burst came from a newborn magnetar, it must have been spinning almost as fast as physics allows, just a few milliseconds per rotation. That kind of spin could power enormous energy release through its magnetic field and radiation. But to keep that up for nearly 7 hours? That would make it the most extreme magnetar we've ever seen, by a long shot. The problem is the data doesn't clearly support or rule out this idea. There's no obvious signature to confirm it. So in the end, we're left with two wild possibilities, and a cosmic mystery that still refuses to settle. And then there's the supernova problem. Gamma-ray bursts caused by collapsing stars are almost always followed by a type IC supernova, a bright flash of visible light marking the star's final explosion. But when astronomers turned their most powerful optical telescopes toward the location of the marathon burst, they saw nothing. No supernova, no flash. Just the fading afterglow of the burst itself. This leaves us with a few possibilities. Maybe the explosion happened in a very faint or dusty galaxy, and the supernova was simply hidden behind layers of dust or too dim to detect. Or maybe the star collapsed directly into a black hole without any outward explosion at all. A silent, total implosion with no light show. There's also a chance that the supernova was just too strange, slow, drawn out, or dim in unexpected ways. And by the time telescopes looked, the key moment had already passed. We had no idea that the marathon burst would change our ideas about how long a star crash can last. We learned that cosmic engines can run for a lot longer than we thought possible. It also showed us that there isn't a clear line between regular GRBs and other strange events, such as ultra-long GRBs, tidal disruption events, and strange collapses. It also showed how important it is to do follow-up studies in real time. We would not have seen this at all if Swift hadn't been looking and ground-based telescopes hadn't followed up. It wasn't just a fireworks show. It lasted for 7 hours and was caused by either a star the size of a small galaxy or a magnetar that was stronger than it looked. SN 2006 GI, the star that killed itself with antimatter. A lot of stars die quietly. A few of them end with a supernova. But SN Ketoiser Hat G? This one really went nuclear. It didn't just blow up. A pair instability supernova, which is the rarest type of supernova in the universe, may have been involved in the way it went out. And that word does sound strange, because it does. Antimatter could have been what caused this explosion. Nicknamed the star that killed itself with antimatter, SN 2006, GY wasn't discovered with grand fanfare. It was found in 2006 by an amateur astronomer in California scanning the night sky. But the moment professional observatories pointed their instruments at it, jaws dropped. This explosion wasn't like the others. About 100 times brighter than a normal Type 2 explosion, it was out of this world. The light curve, or how bright it changed over time, was unlike anything that had ever been seen. It shone brightly for more than 70 days. What was this thing then? To understand SN 2006, we must first look at its parent star, the object that was doomed to explode. A lot of math tells scientists that the first star was about 100 to 250 times heavier than the Sun. That's not just a heavyweight, it's almost a galactic giant. These days, stars that are heavy are not common in the world. They don't stay stable for long, lose mass quickly, and don't usually last long enough to explode in this way. But this one did. It likely belonged to a metal-poor environment, where the star could maintain its mass long enough to grow truly colossal, setting the stage for something violent and strange. Usually a star's core falls when it runs out of energy and joins all the elements together to make iron. This is how most supernovae happen. The rules change when a star is this big, though. The temperatures inside SN 2006 GY's core got so high, more than 1 billion Kelvin, that high-energy gamma rays changed into pairs of particles and antiparticles called electrons and positrons. This part is about pair instability. The star's core was held up by those gamma rays. The core pressure dropped, though, because they used up all their energy making matter and antimatter quickly. Without that pressure, gravity took over. The star contracted violently, heating things up even more, igniting runaway fusion, and finally blowing the star to pieces. This wasn't a core collapse supernova. It was total annihilation. No neutron star, no black hole. The entire star was vaporized, down to atoms, all because it turned its own light into antimatter and collapsed under the weight of that transformation. We think this is one of the only times we've directly seen a pair instability supernova. If it's true, it would be a rare event in the history of astronomy. The fact that the star that killed itself with antimatter was a pair instability event proves that these kinds of blasts still happen in the universe we live in now. We thought they were only found in the early universe, when stars were bigger and didn't have as much metal. Over 100 solar masses worth of heavy elements, like nickel and iron, were created by this type of explosion. This may help explain how they spread through the early universe. There are still stars today that can trigger this kind of fate. They might be hiding in certain galaxies, in low metallicity pockets, waiting for their antimatter-driven apocalypse. This part really confused science. The blast took place in NGC 1260, a galaxy 240 million light-years away. In terms of space, that's pretty close. But the supernova was so bright that novice telescopes could quickly see it. It was as bright as a whole galaxy. Along with the spectrum, it was strange. It had a lot of hydrogen, which is not common for a GRB or even some types of supernova. Some people even wondered if it was really a supernova because it lasted so much longer than they thought it would. Some thought it might have been a tidal disruption event in which a black hole tore apart a star, but there was no black hole in sight. Others said that the blast would have heated up a huge ring of gas around the star. But the most consistent explanation remains: a pair instability supernova, where light becomes matter, antimatter forms, and the core eats itself alive. The star that killed itself with antimatter doesn't just set a brightness record, it will take us back in time to see what the first stars might have looked like as they died. Population 3 stars, which are very big and made of pure hydrogen, probably burst in this way in the early universe. Max J 0717, the cosmic train wreck. If the world had a demolition derby, Max J 0717.5 plus 3745 would be the big fiery mess in the middle of it. This galaxy cluster isn't just hitting another cluster, it's in the middle of at least 4 clusters hitting each other at the same time. an actual pile-up of the stars. A cosmic car crash on a level that our brains have trouble understanding. Astronomers called this part of space the cosmic train wreck because it is so disorderly, violent, and huge. Let's find out why the cosmic train wreck is not only one of the strangest things that has ever happened in space, but also one of the most important cosmic labs we've ever found. The cosmic train wreck is a colossal galaxy cluster merger located about 5.4 billion light-years away in the constellation Auriga. It was discovered as part of the Massive Cluster Survey. That's where it gets its name. A project focused on finding the biggest, most distant cosmic structures. What makes the cosmic train wreck so extraordinary is that it's not just a single merger. It's 4 separate clusters colliding all at once. And they're not coming together quietly. These clusters are smashing into each other at speeds over 3,000 kilometers per second. That's more than 6.7 million miles per hour. Even more intense, the collision isn't happening in a clean, straight path. It's messy. The motions are chaotic, coming in from different directions, tangled and unpredictable. The result is a violent, multi-directional cosmic crash involving galaxies, hot plasma, dark matter, and intense radiation, all swirling in a chaotic mix. It's not just a collision, it's a 4-way galactic demolition derby. The cosmic train wreck is also home to one of the longest known gravitational lensing arcs ever recorded. As the clusters collide, their immense mass distorts the fabric of space-time itself. That warped space bends and magnifies the light from galaxies even farther behind them, like a natural zoom lens. Because of this, the cosmic train wreck has become one of the Hubble Space Telescope's most important targets. Its lensing properties allow astronomers to see galaxies over 13 billion light-years away, helping us look back toward the early universe. The way that the cosmic train wreck tells dark matter apart from regular matter is one of the strangest things about it. The hot gas, normal matter, interacts and slows down when groups crash into each other, like 2 fog banks smashing into each other. Dark matter, on the other hand, doesn't hit anything. It just moves through. This makes a strange imbalance. The gas moves behind, while the galaxies and dark matter move ahead. Astronomers can make a map of where the dark matter is by looking at this split with gravitational lensing and X-ray cameras like Chandra. The cosmic train wreck is one of the best versions of this ever seen. It's not just a crash, it's an X-ray of the universe that shows us what's going on below galaxies that we can't see. Because of the scale and violence of the collision, the cosmic train wreck is filled with hot plasma, gas heated to over 100 million degrees Kelvin. That makes it glow in X-rays, and it creates giant shockwaves as the different clusters punch through each other. These shockwaves are so powerful, they accelerate particles to near-light speeds, turning the region into a cosmic particle accelerator. These particles emit radio waves, which we've detected using instruments like the Very Large Array, VLA, and LOFAR. The cosmic train wreck isn't just massive, it's warping the universe itself. It's one of the strongest sources of the Sunyaev-Zeldovich effect ever recorded. That's when hot gas in the cluster actually distorts the cosmic microwave background, the faint glow left over from the Big Bang. In other words, the wreckage of this merger is literally bending the oldest light in the universe as it passes through. Every way you measure it, the cosmic train wreck breaks the scale. It's one of the most massive galaxy systems ever discovered. It's also one of the most chaotic, with 4 clusters smashing together in a multi-directional high-speed collision. It's a goldmine for studying how dark matter behaves during violent events, acting like a natural physics experiment on a cosmic scale. As a gravitational lens, it lets us peer deeper into the early universe than almost any other structure. And it's a real-life lab for extreme physics. Shockwaves, plasma turbulence, and intergalactic particle acceleration are all happening here. But maybe the most mind-bending part. This isn't a quick explosion or a brief flare. Unlike a supernova or a black hole burst, Max J0717's chaos unfolds on a slow billion-year timescale. This cosmic train wreck has been tearing itself apart for eons, and it's still not finished. The cosmic train wreck isn't done crashing. The galaxy clusters involved are still in the middle of their collision, and they won't fully merge and settle for billions more years. When they finally do, they're expected to form one enormous megacluster, potentially one of the most massive gravitational structures in our cosmic neighborhood. Until then, astronomers will keep turning their telescopes toward this ongoing disaster. They're using it to study how structure forms on the largest scales, to observe how dark matter behaves during high-speed collisions, and to look deeper into the early universe using the natural magnifying power of gravitational lensing. The cosmic train wreck is more than a cosmic wreck. It's a live lab for the deepest questions in astrophysics. PDS 70-cent disk, the Moon Factory. It's not just a baby world. It is a young planet with a disk around it. Right now, the disk may be making moons. Scientists say that PDS 70 cents is the first proven workshop for making moons that has ever been seen outside of our solar system. Located about 370 light-years away in the constellation Centaurus, the star system PDS 70 is a young dusty nursery, a cosmic cradle for planets. But what astronomers found in this system wasn't just ordinary planetary formation. Around one of its gas giant planets, PDS 70c, they discovered a circumplanetary disk, a swirling ring of gas and dust, just like the one Saturn has, except this one is still forming. It's not a moon that exists, it's a moon being born. PDS 70 is a very young star, just about 5 million years old, a newborn by cosmic standards. Around this star, astronomers had already discovered two gas giant planets, PDS 70b and PDS 70c, both roughly the size of Jupiter. But the real surprise came when they pointed the Atacama Large Millimeter/Sub-Millimeter Array at the system. Using ALMA's incredibly sharp radio vision, scientists detected a large disk of material orbiting PDS 70c, separate from the star's larger protoplanetary disk. This meant one thing: this planet wasn't done growing, and neither were its moons. Consider how planets are made. A ring of gas and dust forms around a young star. Planets are made from groups of matter that gather in that ring. But when a planet gets big enough, it starts to pull in its own small disk called a circumplanetary disk, which works like a small solar system. That's where moons are made. Jupiter's largest moons, Io, Europa, Ganymede, and Callisto, are thought to have formed from a planetary ring billions of years ago in our own solar system. We have never seen one happen, though, up until PDS 70 cents. This is the first time that scientists have ever taken a picture of a circle around a planet as it comes together. Not just a weak hint either. This disk has enough stuff in it to make up to 3 rocks the size of our moon. While PDS 70b and PDS 70c are both massive gas giants, only PDS 70c has a detectable circumplanetary disk. That's weird. Both planets formed in the same environment, yet only one is building moons. PDS 70b orbits closer to its star, and it likely lost its surrounding disk due to strong radiation or tidal forces. But PDS 70 cents, sitting farther out, held onto its disk, protected by distance. That extra space made all the difference. It placed PDS 70 cents right in the sweet spot for moon formation, not too hot, not too close, a true Goldilocks zone. The disk around PDS 70c spans about 1.2 astronomical units, roughly the distance from Earth to the Sun. That's enormous when compared to the planet itself. Inside this swirling disk, dust grains are starting to clump together, potentially forming the seeds of future moons. Gas is spiraling inward, feeding the planet and shaping its surrounding magnetic environment. Meanwhile, turbulence and heat are working together to mold the early structure of what could become a full satellite system. It's like watching Jupiter form all over again. Only this time, it's happening 370 light-years away, and we're seeing it unfold in real time. And the tools we're using, like ALMA and the Very Large Telescope, are just beginning to scratch the surface. With sharper eyes on the way, like the Extremely Large Telescope and the James Webb Space Telescope, we may soon be able to image individual moon embryos forming inside PDS 70 centimeters disk. This single planet is helping us tackle some of the biggest open questions in planetary science. How do gas giants get their moons? Do all large planets form surrounded by these dusty, gas-rich circumplanetary disks? And if so, Could exomoons be common throughout the galaxy, just waiting to be found? PDS 70 might be the first real glimpse at the answers. If PDS 70 disk results in several moons, it would support the idea that Jupiter's and Saturn's satellite systems weren't freak accidents. They were the default outcome of giant planet formation. This discovery also opens the door to something astronomers have long dreamed of: finding exomoons. They're much harder to detect than exoplanets, smaller, dimmer, and easily lost in the glare of their host planet. But now we know where to look, around young gas giants still wrapped in the dusty, glowing leftovers of moon-making material. PDS 70C's moon factory isn't just exciting, it's a major milestone in observational astronomy. First confirmed circumplanetary disk? Check. Live footage of moons forming? Check. A system that mirrors how our own Jupiter and its moons may have formed? Absolutely. And all of this was discovered less than a decade ago. As our instruments sharpen and our telescopes evolve, we may not just spot exomoons. We might actually watch one form, grain by grain, until it becomes a world of its own. PSRB 1257+12, the zombie solar system. There are solar systems that start out as rings of dust that are calm and moving. Some people come back from the dead. Welcome to PSRB 1257+12, a pulsar with a strange past and a much stranger future. We're not just looking at any planetary system here. It's the first proven system of planets outside of our solar system, and it circles around the leftovers of a dead star. The first alien worlds we ever found weren't orbiting a sun-like star. They were circling a spinning corpse, beaming radio pulses like a lighthouse in deep space. The zombie solar system is a millisecond pulsar, located about 2,300 light-years away in the constellation Virgo. It spins on its axis roughly 161 times per second, an incredibly fast rate, even for a pulsar. The thing's beginning is what makes it both scary and beautiful. Pulsars are the cores of huge stars that have dropped to the ground after exploding in supernovae. A neutron star is all that's left. It's about the size of a city and has more mass than the Sun. It spins quickly and sends out radio waves from its magnetic poles. It was found that this particular pulsar, B1257+12, had timing problems. Astronomers at first thought it was broken gear. After some thought, it became clear that the waves were being moved by planets. In 1992, something extraordinary happened. Astronomers Alexander Wolszczan and Dale Frail announced the first confirmed discovery of exoplanets, but not around a sun-like star. These planets were found orbiting a pulsar, a rapidly spinning dead stellar remnant. They detected 3 planets in total. The first was Drauga, also known as B1257+12b, a tiny world only twice the mass of the Moon. Then came Poltergeist, or B1257+12c, about 4 times the mass of Earth. And finally, Phobetor, B1257+12 degrees, roughly Earth-sized and orbiting farther out. The names themselves, drawn from myth and ghost stories, fit the tone perfectly. These weren't lush, habitable Earths. These were rocky survivors clinging to a system born from a supernova, planets orbiting the undead. Imagine Earth orbiting a lighthouse that blinks 161 times per second, not glowing with gentle sunlight, but blasting out X-rays and deadly radiation. That's what it would be like to live near a pulsar. These objects form from supernova explosions so violent they should vaporize any nearby planets or fling them out of orbit completely. So how are these planets still here? There are 2 leading theories. One is second-generation formation. After the supernova, some of the leftover debris may have fallen back toward the neutron star, forming a disk of gas and dust. Over time, that material cooled and clumped into brand new planets, worlds born from the wreckage of a dead star. The other theory is a survivor scenario. The zombie solar system might have once been part of a binary system. When its companion star was destroyed or disrupted, the pulsar could have pulled in matter from it, forming a disk. From there, new planets may have formed, or older ones were reshaped by the chaos. Either way, these aren't planets that existed before the star died. They're either survivors of hell or children of it. And make no mistake, These worlds are completely inhospitable. There's no sunlight to warm them. The environment is soaked in high-energy radiation. The pulsar's extreme gravity and magnetic fields likely keep these planets tidally locked, constantly bombarded by stellar wind and stripped of any atmosphere they might have had. They're not just aliens, they're apocalyptic. Yet their very existence is a cosmic paradox. How can something so Earth-sized, so stable in orbit, exist in a place so violent? One of them, Draugr, is the least massive exoplanet ever confirmed, with a mass only twice that of the Moon. It shouldn't even be detectable. Yet the precision of pulsar timing is so exact that even a small planetary nudge shows up. That's the incredible thing about pulsars. They act like natural atomic clocks. Their pulses are so precise that even the tiniest gravitational tug from an orbiting planet throws off their rhythm, making them perfect tools for detecting hidden worlds. And when astronomers found planets around PSRB 1257+12, it shattered everything we thought we knew about where planets, and maybe even life, could exist. Before this discovery, most scientists assumed exoplanets would orbit stars like our Sun in calm, orderly systems. Instead, the very first planets we found were in a zombie solar system, circling the glowing corpse of a dead star. That changed the game. It proved that planet formation is way more resilient than we thought. It showed that new worlds can rise from the ashes of old ones, second-generation planets forming after a supernova. And it forced astronomers to search in stranger places, around white dwarfs, neutron stars, even black hole binaries. The universe had just delivered its first lesson in humility, and it started with the dead. XTE J1739-285, the pulse limit breaker. There's fast, and then there's way too fast. XTE J1739-285 is a neutron star that may have gone faster than one of the fastest speeds ever recorded in the history of physics. Based on what we know so far, this star spins so fast that it could be breaking the rules of physics. Nicknamed the pulse limit breaker, this object isn't just extreme. It's a candidate for the fastest spinning object in the known universe. There is a catch, though. We're not even sure it should exist. A neutron star and a partner star are locked in a tight gravitational hug in the pulse limit breaker. This type of system is called a low-mass X-ray binary. The neutron star is what's left over after a supernova, a collapsed stellar core with the mass of the Sun squeezed into something the size of a city. It's one of the densest things in existence. If you dropped a sugar cube-sized chunk of it onto Earth, it would weigh 1 billion tons. But this isn't just any neutron star. It's one that is actively feeding off its companion star, drawing in matter and spinning faster and faster, like a ballerina pulling in her arms. In 2007, astronomers using NASA's Rossi X-ray Timing Explorer RXTE detected something bizarre while studying this system. Burst oscillations, brief flickers in X-ray light, suggesting the star was spinning at 1,122 rotations per second. That's 67,000 revolutions per minute, or one rotation every 0.00089 seconds. The neutron star's edge would be going at a speed that is a big part of the speed of light at that speed. If this is true, it would be the fastest spin ever seen in a neutron star. It would beat the speed demon, which spins at 716 times per second, to the top spot. Neutron stars are not the same as other stars. How fast they spin is limited by how much centrifugal force their very dense matter can take before it breaks apart. A hard limit is thought to be between 1,000 and 1,200 spins per second by theoretical models. Beyond that, the star's crust would break apart because gravity would not be able to hold it together. So, if the pulse limit breaker is really spinning at 1,122 Hz, it's teetering on the edge of total physical breakdown. It means we may be looking at a neutron star that's dancing right on the knife edge of physics, the closest thing to a natural speed limit for matter. The signal detected in 2007 was extremely brief, lasting just a few milliseconds, and has never been observed again. Some astronomers argue it could have been noise, a data artifact, or a rare one-time phenomenon not tied to rotation. Others suggest it could have been the result of hotspots on the neutron star's surface, created by uneven accretion, flickering as the star rotates. But there's no denying something strange was going on. And if that 1122 Hz signal from the pulse limit breaker is real, it changes everything. A spin that fast would push a neutron star to its absolute physical limit. It would confirm the theoretical maximum for how fast these objects can rotate before breaking apart. It would also force scientists to update the equations of state, the models that describe how matter behaves under nuclear-level pressure. And most intriguing of all, it could support the existence of quark stars, ultra-dense objects made of free-floating subatomic particles, capable of surviving spin rates that would tear normal neutron stars apart. In other words, the pulse limit breaker might not just be a record-breaking pulsar, it could be a window into a new state of matter. That's why spinning neutron stars are so valuable. They act as natural laboratories, letting astronomers test theories of gravity, probe the limits of matter under extreme conditions, and explore how fast and how violently the universe can push its own laws. XTJ1739-285 stands right at that edge. Even if it turns out to be a rare fluke, it still tells us something vital. The universe is always experimenting, always pushing the envelope, always daring us to keep up. It's becoming more and more clear that the universe we live in is not a calm, organized place. It's crazy, random, and full of crazy events that don't make sense. From cosmic cannibals to stars that come back to life after death, these times are more than just records. They're warnings, mysteries, and calls to keep exploring. If this amazed you, there's a lot more out there beyond the stars. Please remember to like, subscribe, and comment if you want to join the discussion on Beyond Horizons, where you can always reach out and touch the world.